Hello everyone, I'm Prakriti and I'm here to tell you about a very common issue we face every day, wasting electricity without even realizing. As small as it may look, but the problem is larger, and that is why Mission Life has it in its charter.
सरकार का जोर बिजली का उत्पादन बढ़ाने के साथ ही बिजली की बचत करने पर भी है। बिजली बचाना यानी भविष्य सजाना।
Carelessly keeping that switch on may mean nothing to us, but for some, electricity is a ray of hope. On an average, our households waste about 35% of electricity every month. This doesn't just raise our own expenditure manifolds, but burdens the country, forcing it to rely on non-renewable energy. The result, polluting the environment. Lifestyle for Environment is a mission to identify simple acts in our daily lives that can contribute significantly to tackle climate change. Turn off the lights while leaving a room, switch to energy-efficient appliances and LED lights, unplug devices when not in use. Use natural light sources whenever available. And keep your air conditioner at 24 degrees. Save energy for better tomorrow.
मिशन लाइफ का मंत्र है लाइफस्टाइल फॉर एनवायरनमेंट। पृथ्वी पर रहने वाले प्रत्येक व्यक्ति को व्यक्तिगत प्रयासों की कामना के साथ ही आज ये मिशन लाइफ का ये विजन दुनिया के सामने रख रहा हूँ।
फ्रेंड्स, प्रधानमंत्री नरेंद्र मोदी जी के मिशन लाइफ के संकल्प को आप सजग रहकर मजबूती दे सकते हैं और रोजाना के कामकाज में कुछ आसान उपायों से अपना योगदान दे सकते हैं। कैसे, आइए जानते हैं। पौधों, फर्श और वाहनों आदि में पानी के उपयोग के लिए होस पाइप या पाइप के बजाय बाल्टी का उपयोग करें। एसी और आरओ से निकले पानी का पुनः उपयोग करें। जल इकाइयों को रिचार्ज करने के काम को बढ़ावा दें और औरों को भी प्रेरित करें। सब्जियों को साफ करने के बाद पानी का पुनः उपयोग पौधों को पानी देने या ऐसे किसी अन्य कार्यों के लिए करें। घर, स्कूल और कार्यालयों में वाटर हार्वेस्टिंग बॉडीज का निर्माण करवाएं। लाइफस्टाइल फॉर एनवायरनमेंट अपनाइए। मिशन लाइफ से दुनिया बेहतर बनाइए।
पर्यावरण, वन और जलवायु परिवर्तन मंत्रालय, भारत सरकार द्वारा जनहित में जारी।
मेरे प्यारे देशवासियों, एक छोटी सी अपेक्षा आज आपसे सामने रखना चाहता हूं। इस 2 अक्टूबर को हम भारत को सिंगल यूज प्लास्टिक, क्या इससे देश को मुक्ति दिला सकते हैं?
माननीय प्रधानमंत्री श्री नरेंद्र मोदी जी के मार्गदर्शन अनुसार हमें भारत को सिंगल यूज प्लास्टिक मुक्त बनाना है और इसके लिए सबकी भागीदारी आवश्यक है।
बेटा जी, ये रहे आपके प्लास्टिक के डिब्बे, प्लास्टिक की प्लेट्स, स्ट्रॉ और ये रहे आपके प्लास्टिक के कप।
कितने हुए?
800 रुपए।
अरे रुको रुको, ना मैं ये लूंगी ना मैं ये लूंगी और ये तो बिल्कुल भी नहीं लूंगी।
पर क्यों?
जानते नहीं कि सिंगल यूज प्लास्टिक का इस्तेमाल नहीं करना चाहिए।
सिंगल यूज प्लास्टिक एक बार इस्तेमाल करने के बाद फेंक दिए जाते हैं और हमारे वातावरण को प्रदूषित करते हैं।
इसलिए भारत सरकार ने इसके इस्तेमाल पर 1 जुलाई 2022 से रोक लगाई है। ये सिंगल यूज प्लास्टिक पर्यावरण में मत फैलाओ। कुछ लेने जाओ तो कपड़े के बैग को लेके जाओ और पॉलिथीन को अपने जीवन से हटाओ। प्लास्टिक के बर्तनों से अपना रिश्ता तोड़ो। स्टील, ग्लास, लकड़ी और मिट्टी के बर्तनों से नाता जोड़ो।
राइट।
प्लास्टिक के कूड़े को जल में कभी ना मिलने दे। पानी के जीवन को खतरे में ना पड़ने दे। मिशन लाइफ को अपने जीवन शैली में लाएं। आओ मिलकर प्रो प्लैनेट पीपल बन जाएं और पर्यावरण को सिंगल यूज प्लास्टिक मुक्त बनाएं।
पर्यावरण, वन एवं जलवायु परिवर्तन मंत्रालय, भारत सरकार द्वारा जनहित में जारी।
Hello everyone, I am Prakriti. Mobile phones and electronic devices have become essential in our lives. But do you know that e-waste generated from these is very harmful for our environment? Our Prime Minister Shri Narendra Modi has come out with solutions to address these problems in Mission Life.
लोग जानना चाहते हैं कि अपने खुद के प्रयत्न में या परिवार के साथ और अपने समुदाय के साथ मिलकर वो कौन से कदम उठा सकते हैं जिससे धरती की सुरक्षा हो सके, इस पृथ्वी की सुरक्षा हो सके। इन सारे सवालों का जवाब मिशन लाइफ में है।
Life, Lifestyle for Environment is a mission to help you identify simple acts in our daily lives that can contribute significantly to tackle climate change. We too have a significant role to play to mitigate our carbon footprint. Come and let us work together to reduce the e-waste for a safe environment. Do not throw the e-waste here and there. Utilize the e-recycling units to protect our environment. Use rechargeable batteries. Prefer using cloud storage over a pen drive or a hard drive. Use mobile phones and electronic items to their full life cycle. These are few small steps that can lead to a great improvement in mitigating chemical leakage in the environment. Let's choose a chemical-free environment. Choose life. Hello everyone, I am Prakriti. Our Swachhata Abhiyan is bringing so much positive change and the world is talking about our conviction to Swachhata.
देश के हर कोने में, समाज के हर वर्ग के लोगों ने स्वच्छ भारत के उनके सपने को पूर्ण करने के लिए जो भी कर सकते हैं, जितना कर सकते हैं, क्षमता से कभी-कभी अधिक करने का भी प्रयास किया है।
In fact, our Prime Minister has identified its significance in Mission Life. Lifestyle for Environment is a mission to help you identify simple acts in our daily lives that can contribute significantly to tackle climate change. Practice segregation of dry and wet waste at home. Recycle and reuse old newspapers. Set printer default to double-side printing. Donate our old clothes and books. Do not throw waste in public spaces. एक कदम स्वच्छता की ओर।
शरीर को स्वस्थ रखने के लिए योग जरूरी है। शरीर के पोषण के लिए जैसे मिलेट्स जरूरी हैं, ऑर्गेनिक और नेचुरल फूड जरूरी हैं, ऐसे ही प्रकृति को स्वस्थ रखने के लिए और प्रदूषण को नियंत्रित करने के लिए जरूरी है कि हम वृक्ष लगाएं। अपने घरों में तुलसी, अश्वगंधा, गिलोय और नीम जैसे पेड़ पौधे लगाएं और जानवरों की खाल से बने प्रोडक्ट से दूरी बनाएं। ध्यान रखिए, अगर हम प्रकृति को बचाएंगे तो ही लाइफ को बेटर बनाएंगे।
क्या बात है, बालकनी का असली फायदा तो आप उठा रहे हो, सब्जियां उगा रहे हो।
हाँ, और इसी बहाने थोड़ा मन भी बहल जाता है।
और आंटी, लाइफ में कुछ यूजफुल करने को भी मिल जाता है।
खाद क्या डालोगी?
ऑर्गेनिक कंपोस्ट, किचन और फूड वेस्ट से तैयार करके।
ये सब कहाँ से सीखा?
स्कूल से।
मुझे भी सिखाओ, आखिर पड़ोसी ही पड़ोसी के काम आता है ना?
आप भी नेचर के करीब आइए, लाइफ को बेटर बनाइए।
അത് ബൈക്കാണ് കൂടുതൽ സൗണ്ട്, കാറാണെങ്കിൽ എടുത്തു പോകണം, എക്സ്പെൻസ് കൂടുതൽ, സൈക്കിളിന് എക്സ്പെൻസ്, പൈസ വേണ്ട, വളരെ ഈസിയാണ്. നമുക്ക് കുറച്ച് എക്സസൈസുമായി, ശരീരത്തിന് എനർജിയായി, നമ്മൾ ചവിട്ടിപ്പോയി ശാന്തമായിട്ട് പോയിട്ട് മര്യാദയ്ക്ക് നമുക്ക് തിരിച്ചു വരാം. പോലീസിനെ പേടിക്കണ്ട, ലൈസൻസ് കാണിക്കണ്ട, ഒന്നും കാണിക്കണ്ട. ഇത് സൈക്കിൾ ഫ്രീ. വേൾഡ് ഓഫ് സൈക്കിൾ ലോകത്തെല്ലാവരും ഉപയോഗിക്കണമെന്നാണ് ഞാൻ പറയുന്നത്. സൈക്കിളാണ് വെരി ഇമ്പോർട്ടൻറ്റ്. മൈ ലൈഫ് എന്ന് പറയാം. അവനവൻ്റെ ആരോഗ്യത്തിന് ഏറ്റവും വലുത് സൈക്കിളാണ്. ഇന്ന് ലോകത്ത് ഏറ്റവും കൂടുതൽ സൈക്കിൾ ഉപയോഗിക്കുന്ന ഒരു രാജ്യമാണ് ചൈന. അത് കഴിഞ്ഞിട്ട് ഇന്ത്യയിൽ അധികം ഉപയോഗിക്കണമെന്നാണ് എൻ്റെ ഒരു ஆமாம். ஏசியில் வந்து உடம்புக்கு எல்லாருக்கும்
இந்த மாதிரி கார்பன் மோனாக்சைடு பைக்லேருந்து வர்றதெல்லாம் நமக்கு நல்ல விஷயம். நானும் நாளையிலேருந்து ബൈക്കിൽ പോകാം, സൈക്കിളിലേ പോകാം.
ഓക്കെ,
താങ്ക് യു.
നിങ്ങളുടെ അഭിപ്രായത്തിനോട് ഞാൻ 100% യോജിക്കുകയാണ്. ഞാനും നാളെ മുതൽ ഇത് പിന്തുടരും. താങ്ക് യു. താങ്ക് യു ഫോർ ദ ഇൻഫർമേഷൻ.
നല്ല ഇൻഫർമേഷൻ. ഞാനൊരു സൈക്കിൾ
ശരി.
ഓക്കെ കാര്യം അറിയാൻ വേണ്ടി വന്നതാണ്. മാഡത്തിന്റെ വീട്ടിൽ ഏത് ടൈപ്പ് ഓഫ് ലൈറ്റാ ഇപ്പോൾ യൂസ് ചെയ്യുന്നത്? പഴയ CFL യൂസ് ചെയ്യുന്നത്. പഴയ CFL ഇലക്ട്രിസിറ്റി ബില്ലൊക്കെ എത്ര വരും? എന്തായാലും 2000 മുകളിലാണ് വരിക. മാഡം നമ്മുടെ മിനിസ്ട്രി വരെ പറയുന്നുണ്ട് നമ്മുടെ ഇങ്ങനത്തെ പഴയ ലൈറ്റൊക്കെ മാറ്റിയിട്ട് LED ലൈറ്റ്, സ്ട്രീറ്റ് ലൈറ്റ് അതൊക്കെ വേണം യൂസ് ചെയ്യാൻ വേണ്ടിയിട്ട്. AC ഉണ്ടോ വീട്ടിൽ? വീട്ടിൽ AC ഉണ്ട്. ആ AC അതേപോലെ യൂസ് ചെയ്യുമ്പോൾ പവർ സേവിങ് മോഡിൽ വേണം ഇടാൻ വേണ്ടിയിട്ട്. അപ്പോൾ നമ്മൾ ഈ LED ലൈറ്റൊക്കെ ഉപയോഗിച്ച് കഴിഞ്ഞാൽ ഇലക്ട്രിസിറ്റി ബില്ലൊക്കെ കുറയും? തീർച്ചയായും. നമ്മുടെ ഇലക്ട്രിസിറ്റി ബില്ല് മാഡത്തിന് 2000 അല്ലേ വരുന്നത്? അതെ. അത് നേരെ പകുതിയാവും. ഒരു 500 അടുപ്പിച്ച് വരുത്തുള്ളൂ. നമ്മുടെ എനർജിയിൽ നമുക്ക് അപ്പം LED ലൈറ്റ് യൂസ് ചെയ്യണം മാഡം. അപ്പോൾ എന്തായാലും ഞാൻ എൻ്റെ ഭർത്താവിനോട് പറഞ്ഞു എന്തായാലും എല്ലാം ഞാൻ LED ലൈറ്റ് ആക്കാൻ പോകും. അപ്പോൾ ഈ LED ലൈറ്റ് ഉപയോഗിച്ച് നമ്മൾ കുട്ടികൾക്കും പഠിക്കാൻ പറ്റില്ലേ? പിന്നെ തീർച്ചയായും. അവരുടെ ഈവൻ നമ്മുടെ എന്താ പ്രകാശം തന്നെ അവരുടെ കണ്ണുകൾക്ക് നല്ലത് ഇത് തന്നെയാണ്. അപ്പോൾ അധികം ഇറിറ്റേഷൻ ഉണ്ടാക്കത്തില്ല. താങ്ക് യു സോ മച്ച്. ഓക്കെ മാം.
मिशन लाइफ का मंत्र है लाइफस्टाइल फॉर एनवायरमेंट। पृथ्वी पर रहने वाले प्रत्येक व्यक्ति को व्यक्तिगत प्रयासों की कामना के साथ ही आज ये मिशन लाइफ का ये विजन दुनिया के सामने रख रहा हूं।
My dear Prakriti, remember what you have to do on earth?
Yes, Mother. I will educate people with love so that they understand mission life and maintain the environmental balance by adopting environment-friendly lifestyle.
My child, these 3 things will help you on your journey. First is the tiara of flowers. This will keep you happy and energetic. Second, this badge of life, which will remind people of life, lifestyle for environment. You can also give this badge to people who contribute for the betterment of our planet. And third, this bag of hope. Whenever someone harms the environment, you can take out eco-sustainable alternatives from the bag and inspire them to adopt Mission Life.
Okay, Mother. Now I will leave for my mission life.
There's one life, but there's one mission. Let's all work for environment, rejuvenation, beloved planet's protection. Adopting environment-friendly lifestyle is our ambition. Say no to single-use plastic. Let's use stairs instead of lift. Save water, segregate waste, reduce overconsumption and reuse again. Together we can, together we will, together we will achieve this ambition. There's one life, there's one mission. Let's all work for environmental rejuvenation, beloved planet's protection.
Let's choose life for Green Planet Vision.
Hello everyone, I'm Prakriti and I'm here to tell you about a very common issue we face every day, wasting electricity without even realizing. As small as it may look, but the problem is larger and that is why Mission Life has it in its charter.
सरकार का जोर बिजली का उत्पादन बढ़ाने के साथ ही बिजली की बचत करने पर भी है। बिजली बचाना यानी भविष्य सजाना।
Carelessly keeping that switch on may mean nothing to us, but for some, electricity is a ray of hope. On an average, our households waste about 35% of electricity every month. This doesn't just raise our own expenditure manifolds, but burdens the country, forcing it to rely on non-renewable energy. The result, polluting the environment. Lifestyle for Environment is a mission to identify simple acts in our daily lives that can contribute significantly to tackle climate change. Turn off the lights while leaving a room, switch to energy-efficient appliances and LED lights, unplug devices when not in use. Use natural light sources whenever available. And keep your air conditioner at 24 degrees. Save energy for better tomorrow.
मिशन लाइफ का मंत्र है लाइफस्टाइल फॉर एनवायरमेंट। पृथ्वी पर रहने वाले प्रत्येक व्यक्ति को व्यक्तिगत प्रयासों की कामना के साथ ही आज ये मिशन लाइफ का ये विजन दुनिया के सामने रख रहा हूँ।
फ्रेंड्स, प्रधानमंत्री नरेंद्र मोदी जी के मिशन लाइफ के संकल्प को आप सजग रहकर मजबूती दे सकते हैं और रोजाना के कामकाज में कुछ आसान उपायों से अपना योगदान दे सकते हैं। कैसे? आइए जानते हैं। पौधों, फर्श और वाहनों आदि में पानी के उपयोग के लिए होस पाइप या पाइप के बजाय बाल्टी का उपयोग करें। एसी और आरओ से निकले पानी का पुनः उपयोग करें। जल इकाइयों को रिचार्ज करने के काम को बढ़ावा दें और औरों को भी प्रेरित करें। सब्जियों को साफ करने के बाद पानी का पुनः उपयोग पौधों को पानी देने या ऐसे किसी अन्य कार्यों के लिए करें। घर, स्कूल और कार्यालयों में वाटर हार्वेस्टिंग बॉडीज का निर्माण करवाएं। लाइफस्टाइल फॉर एनवायरनमेंट अपनाइए। मिशन लाइफ से दुनिया बेहतर बनाइए।
पर्यावरण, वन और जलवायु परिवर्तन मंत्रालय, भारत सरकार द्वारा जनहित में जारी।
मेरे प्यारे देशवासियों, एक छोटी सी अपेक्षा आज आपसे सामने रखना चाहता हूं। इस 2 अक्टूबर को हम भारत को सिंगल यूज प्लास्टिक, क्या इससे देश को मुक्ति दिला सकते हैं?
माननीय प्रधानमंत्री श्री नरेंद्र मोदी जी के मार्गदर्शन अनुसार हमें भारत को सिंगल यूज प्लास्टिक मुक्त बनाना है और इसके लिए सबकी भागीदारी आवश्यक है।
बेटा जी, ये रहे आपके प्लास्टिक के डिब्बे, प्लास्टिक की प्लेट्स, स्ट्रॉ और ये रहे आपके प्लास्टिक के कप।
कितने हुए?
800 रुपए।
अरे रुको रुको, ना मैं ये लूंगी ना मैं ये लूंगी और ये तो बिल्कुल भी नहीं लूंगी। पर क्यों? जानते नहीं कि सिंगल यूज प्लास्टिक का इस्तेमाल नहीं करना चाहिए।
सिंगल यूज प्लास्टिक एक बार इस्तेमाल करने के बाद फेंक दिए जाते हैं और हमारे वातावरण को प्रदूषित करते हैं।
इसलिए भारत सरकार ने इसके इस्तेमाल पर 1 जुलाई 2022 से रोक लगाई है। ये सिंगल यूज प्लास्टिक पर्यावरण में मत फैलाओ। कुछ लेने जाओ तो कपड़े के बैग को लेके जाओ और पॉलिथीन को अपने जीवन से हटाओ। प्लास्टिक के बर्तनों से अपना रिश्ता तोड़ो। स्टील, ग्लास, लकड़ी और मिट्टी के बर्तनों से नाता जोड़ो।
राइट।
प्लास्टिक के कूड़े को जल में कभी ना मिलने दे। पानी के जीवन को खतरे में ना पड़ने दे। मिशन लाइफ को अपने जीवन शैली में लाए। आओ मिलकर प्रो प्लैनेट पीपल बन जाए और पर्यावरण को सिंगल यूज प्लास्टिक मुक्त बनाए।
पर्यावरण, वन एवं जलवायु परिवर्तन मंत्रालय, भारत सरकार द्वारा जनहित में जारी।
Hello everyone, I am Prakriti. Mobile phones and electronic devices have become essential in our lives. But do you know that e-waste generated from these is very harmful for our environment? Our Prime Minister Shri Narendra Modi has come out with solutions to address these problems in Mission Life.
लोग जानना चाहते हैं कि अपने खुद के प्रयत्न में या परिवार के साथ और अपने समुदाय के साथ मिलकर वो कौन से कदम उठा सकते हैं जिससे धरती की सुरक्षा हो सके, इस पृथ्वी की सुरक्षा हो सके। इन सारे सवालों का जवाब मिशन लाइफ में है।
Life, Lifestyle for Environment is a mission to help you identify simple acts in our daily lives that can contribute significantly to tackle climate change. We too have a significant role to play to mitigate our carbon footprint. Come and let us work together to reduce the e-waste for a safe environment. Do not throw the e-waste here and there. Utilize the e-recycling units to protect our environment. Use rechargeable batteries. Prefer using cloud storage over a pen drive or a hard drive. Use mobile phones and electronic items to their full life cycle. These are few small steps that can lead to a great improvement in mitigating chemical leakage in the environment. Let's choose a chemical-free environment. Choose life. Hello everyone, I am Prakriti. Our Swachhata Abhiyan is bringing so much positive change and the world is talking about our conviction to Swachhata.
देश के हर कोने में, समाज के हर वर्ग के लोगों ने स्वच्छ भारत के उनके सपने को पूर्ण करने के लिए जो भी कर सकते हैं, जितना कर सकते हैं, क्षमता से कभी-कभी अधिक करने का भी प्रयास किया है।
Please. Hello. Check it out. Yes, you have to copy it.
In rigorous discussion, exchanged invaluable insights, and formed meaningful connections, all with the shared goal of addressing the critical challenges and opportunities surrounding nitrogen management and sustainability. Throughout the conference, we have explored a wide range of topics, including nitrogen pollution migration strategies, sustainable agriculture practices, innovation technologies, and policies framework at safeguarding our ecosystems and enhancing the food security. We have heard from our leading speakers, each offering their unique perspective and solutions to complex nitrogen related issues facing our planet. Today, on this final day of conference, we have an exceptional lineup of sessions and plan to build up upon the momentum generated thus far. In addition to our informative various sessions, we will also have an ample opportunities for networking and knowledge exchange and collaborative brainstorming. These interactions are essential for interdisciplinary collaboration and driving collective action towards sustainable nitrogen management. Before we commence with today's agenda, I would like to extend my sincere appreciation to all the sponsors, partners, speakers, and attendees for their unwavering support and, their dedication throughout this conference. As we embark on this final day of International Nitrogen Conference, let us reaffirm our commitment to working together towards a future where nitrogen is managed responsibly and ecosystems are protected and food security is ensured for the generation to come. With all these words, I would like to invite Dr. David Cantor, the esteemed chair of International Nitrogen Initiative and Associate Professor of Environmental Studies at New York University, to co-chair the session. Over to you.
Thank you very much. I've never been called esteemed before. I appreciate that. Good morning, everyone. Good morning, everyone. Thank you. Welcome to the final day of the 9th Global Nitrogen Conference. It's my pleasure to moderate this final set of keynote talks. Just a small, not housekeeping, but just to bring to your attention this afternoon. So after this keynote, we'll have another poster session. Then we'll have a final set of oral parallel sessions. And then afterwards, I'm especially excited for this afternoon session because there will be a session here on the emerging messages from the first International Nitrogen Assessment, which many of you have been authors on. And this has been obviously a long-term project that many of us are excited to see come to fruition. And then after that, there will be kind of the first of its kind at a global nitrogen conference, and I'm really excited to see it, which are we've labeled as research agenda discussions. And the rationale behind that is that we come to these conferences and we hear about really exciting, latest cutting-edge research. But we don't often get an opportunity, at least in a more formal group setting, to think about what are some of the future research questions that we should be asking ourselves. And we have a unique opportunity here with so many members of the nitrogen research community and other stakeholders to really think about what are the research directions we should be going in the run-up to the next nitrogen conference. And so we're kind of organizing 3 separate discussions around that idea of what are the future research directions. And they'll be organized there'll be one on crop, livestock, and soil health, one around all the environmental impacts, air, water, climate, biodiversity, and then a third one on society and governance and circular economy. And so I would just encourage you or implore you that, go to those sessions and really think about what are some of the future research directions that we could go in as a community. I think it's an exciting opportunity for us to think about that. So with all that said, I'm honored and excited to introduce the first of the keynote speakers this morning, Martin van Dam from the ULB in Belgium, the university in Brussels that I grew up just around the corner from, the Université Libre de Bruxelles. So it's very exciting to have Martin here. And he will be talking to us today about satellite monitoring of ammonia, the main achievements and promising perspectives. Martin, thank you so much. Welcome.
Good morning, everyone. Thank you very much to the organizer for giving me the opportunity to present our work on satellite monitoring of ammonia. For those who have already been involved in measuring ammonia in situ, this ground-based measurement, it's quite challenging. It's a sticky gas that quickly reacts in the environment. It also interacts with the instrumentation deployed to measure it. And due to its short lifetime, it is also high temporal and spatial variability, which makes the point measurement not always representative for the larger scale. It was really a scientific breakthrough when around 15 years ago, the satellites were shown to be able to measure ammonia. And we have nowadays a constellation of hyperspectral sonders able to measure ammonia. Not all of them are able to provide ammonia dataset, but the vast majority. And this instrument can be on board polar orbiting satellites, which provide readily global distribution, or they can also be more recently on board a geostationary satellite. This satellite always scan the same disk Earth at a much higher temporal sampling. Thus, in this talk, we will mainly see results from the YASI mission and also some results from the CRIS instrument. And we will end it with first result from geostationary mission with the GERS instrument and the forthcoming IRIS instrument. But how does it work? You have the infrared radiation that is emitted by the Earth as any black body, and this radiation is then absorbed and re-emitted by the different constituents of the atmosphere and detected on the detector of the instrument. And then we get this type of spectra that's shown here on top in black. In this spectra, you can directly see the signature of the strong absorber, such as H2O, CO2, ozone. Each molecule has its own spectral signature in this spectrum. And this spectral signature acts as a fingerprint or a barcode that we can recognize and associate to each molecule. And we are fortunate that there are several species having their absorption cross-section inside the atmospheric window, allowing us to monitor it from space, and this includes ammonia. To go from this spectra to distribution, we apply sophisticated radiative transfer retrievals, and then we get this type of global distribution that we can use for environmental analysis, air quality, atmospheric chemistry studies. At ULB, we are working for over 20 years now on the infrared atmospheric sounding interferometer mission. This mission is composed of a series of 3 identical instruments on board the METOP European Polar Orbiting Satellite. The first one was launched in 2008, and then it was followed in 2012 and 2018 by 2 other instruments. This YASI measures the infrared radiation emitted by the Earth perpendicularly to the surface at a relatively small pixel size of around 12 kilometers at the nadir, this perpendicularly, but when you are at the end of the swath, the pixel extend to an elliptical footprint of 20 by 40 kilometers. On the first distribution obtained in 2009, we have improved our retrieval algorithm. We are now at version 4. We have an improved consistency over time, and now we also provide algorithm kernels, allowing to cancel out the effect of the vertical assumption, the vertical distribution of the ammonia in the atmosphere that we have to do to retrieve the total carbon. The retrieval consists in 2 steps. The first one is the characterization of the spectral signature with the calculation of the hyperspectral range index. And this HRI is then converted in the second step into the actual total columns using neural networks. So I could spend the rest of this talk describing this complex graph and explaining how good the retrieval is, but I will not do that because I have a much more exciting application to share with you. And we'll directly dive into the product. The theory of the daily global distribution and the hemispheric time series on top. You can see in March, April, for example, large column over Europe, Northern America, and then we have large column measured over India over during the entire years. In July, large column over the North China plain associated with coke, burning of coke residues. In summer, were the biomass burning in northern hemisphere, boreal region. End of the year, beginning of the next one, slash and burn agriculture in Western Africa. But how to work with such scattering data set? Because usually what we do is that we grid the data on a rectangular latent grid that we have arranged that at the set size, the grid is a set size comparable to the spatial resolution of the instrument. But this only takes into account the location of the center of the observation, the satellite observation, and this is the type of distribution that we get for the Nile Delta in Bali, which is quite nice. But if we want to go beyond native resolution of the instrument, we can explore the fact the location, the shape, and the orientation of the satellite footprint on ground will vary from one orbit to another. Because here we can see what does it give when we aggregate data after 2 days, 3 days, a week, a month, a year, and then 10 years. That's losing the temporal information. We achieve a considerable increase in resolution with this 1 kilometer resolution map. We can identify additional point sources, like shown here, coastal region there. It's important to note that there is no artificial post-smoothing. The smooth appearance of this map is only coming from the methodology applied, the sensitivity of the retrievals, and the fact that we use a large amount of data. And then we get this type of distribution that we've already shown, that we've already seen. But this oversampled map will always be a smoothed representation of the reality. You will see that with this theoretical example. This is indeed the oversampled maps that you obtain when you apply 100,000 measurements of an hypothetical instrument with a varying footprint size on the bound's truth shown here in A. Thus, we can see that it's a smoothed representation of that reality and that we cannot detect the fainter point sources. To go a step further, we have developed and we have used a super resolution technique. It's what we use in image processing, and it aims at building high resolution images based on low resolution representation of the same reality. This is the nice example of the license plate recognition here. For our theoretical example on top, this is what we obtain when we apply the super sampling by iteration, and you can see that we can detect much fainter point sources. If we apply that on real data, and as far as we know, the first time that this was applied on measurement of an atmospheric sounder, we are over one of the main ammonia plants in Ukraine, and this is what we obtain if we grid the Yazi observation. It's the oversampled average. For super sampling, we need a constant underlying distribution. To get that, we will rotate each Yazi observation following the wind speed and the wind direction. And this is what we obtain after the super sampling. And we have done that for each pixel of the world, considering each point of the world as a potential point sources. And we get this type of distribution, and we can zoom on this distribution. Here we are in central US. We zoom for this enhancement. We can see that we are in a highly insular region in Colorado. And if we continue to zoom in, we can see that this hotspot is just above the massive field lots accommodating for thousands of cars. If we go now in another place of the world, we will zoom on Central Asia. We are in the Fergana Valley. This valley is known for its cotton production in the 80s, also partly responsible for the drying of the Aral Sea. And if we desaturate our distribution, we can see that we have a hotspot in a hotspot. And if we zoom in over this region, we are just above an enormous industrial factory, ammonia producer, fertilizer producer, it's Fergana Azot, emitting massive amount of ammonia in the atmosphere. We have analyzed in detail all the globe, and we have now a catalog of over 600 point sources that have been identified, categorized, and quantified with feedlots, pig farming activities, poultry farming, fertilizer plant, also nickel mining in Cuba, for example. We also identify natural point sources. In the natural lake, this is a very specific condition, very high pH, very high temperature. There are flamingos that play an important role in the nutrient cycling in that lake. They are breeding the phytoplankton, and there are also excretion. And the ammonia volatilization there is due to the drying processes of the mudflat that emit shifts here, the decrease of the surface of the lake, which is associated with an increase of ammonia emission. This point source in this catalog has been recently updated within the framework of the World Emission Project. It's an ESA-funded project aiming at stimulating the use of satellite data to constrain emission estimates, and also aiming at disseminating the results to users. We can also analyze the global variability of the fluxes. Because for the super sampling, we need a large amount of data, so we cannot do that on a yearly basis, but we can derive fluxes with the oversampling method and get yearly fluxes. Thus for Italy, the site we just seen together, you can see that we have a relatively constant flux over the years. While in Baku, in Romania, Yazi has identified the closure of the factory in 2013 and the associated drop in ammonia emission. We'll compare our satellite DRR fixes with the EDGAR global emission inventory, and while with a fair agreement for the large majority of the source region, EDGAR vastly underestimated the point source emission. We've also recently compared these satellite derived fluxes with the European Pollutant Release and Transfer Register. It's a register where the factories have to report their emission. And as expected, we don't have a good correlation, and the satellite derived fluxes are higher than what is reported in this register. If we focus on one of the point sources, this is Pisteritz. This is one of the sites that we should have been able to visit at the last nitrogen conference in Germany, but this has not happened. But what happened is that we've been able to make a survey flight over this site with an instrument on board an aircraft, so we can put type of infrared imager and make this type of line flight to have an area surveyed, and then we can detect the plume and the evolution of the plume from the chimney in the atmosphere. And from this type of graph of survey flight, we can derive also the emission fluxes. The aircraft emission fluxes for Pisteritz are slightly higher than what is calculated from the satellite, but they are consistent, and both are much higher than what is reported in the register. Additionally to the emission, what we can also do is estimate the lifetime looking at the decay of the plume. As if we mean rotate the ammonia observation, we can then apply a three-dimensional fit or a two-dimensional fit and derive the atmospheric lifetime. This has been done here for Segunda in South Africa, and this has been done globally by Damers et al. And calculated an atmospheric lifetime of around 2 hours for this type of sources. Let's leave now the point source scale and go at more regional scale, as the satellites provide unprecedented constraint on the distribution at such scale. This is a map that I particularly appreciate, is the amounts of maximum concentration that have been calculated looking at the climatology of the monthly time series. You can see on top that climatology, like for example, for Western Europe, you have 2 peaks associated with the fertilization period. North China playing the peak in July. And Christopher Beat and colleagues have analyzed the temporal variability over South Asia, investigating the 2 main ammonia satellite products from the YASI instrument and the CRIS instrument. And they've shown the discrepancies between the temporal pattern recorded by the satellite and what is currently in the inventories. Making the most of the 15 years of consistent ammonia data, we can also investigate the trends. And we calculate for the 2008-2018 period worldwide decadal increase of 12.8%. We can move to the national scale. Here you have the national trends, absolute trends in colors, and the relative trend indicated in black for the series of countries. And the countries associated with a non-significant trend are hatched. We can further investigate this yearly variation looking at the relative yearly time series relative to 2008. And you can see that over this 15 years period, we have close to a doubling of the atmospheric ammonia for a series of countries, including the United States and China. If we investigate the yearly time series for the countries largely impacted by biomass burning, you can see that Indonesia stands out with the year 2015. And that year occurred a massive fire of land that burned a very large surface layer of around 40 centimeters of peatland that burned and released a tremendous amount of ammonia in the atmosphere. Pakistan and India. Pakistan present one of the largest absolute trends due to overconsumption of synthetic fertilizer. And India is a more complex case. The national scale does not present a significant trend. And this is due to the distinct spatial pattern between the northwestern part of the country, representing an increasing trend, and the southeastern part of the country that presents a decreasing trend. And tentative explanation is that, in fact, India took several measures to reduce nitrogen pollution, and one of them was to force manufacturers to produce urea coated with neem oil. And we have already discussed that. This confirms this type of inhibitor, the efficiency of this type of inhibitor is depending on the soil pH and could also lead to increase of ammonia emission over alkaline soil. And it's therefore interesting to know the spatial correlation between the soil pH in the region and the ammonia trends reported by ESD. The last temporal scale that has not been investigated until recently is the day-to-day variability of ammonia over the course of the week. For NO2, it's widely known that you have a strong weekend effect with a decrease of NO2 concentration in column due to the decrease of anthropogenic emission on Saturday and Sunday. And we are not expecting to find a similar weekend effect for ammonia. However, we have unambiguously detected a weekend effect with a decrease of ammonia on Sunday, Monday. Yearly average, we have a decrease of 15%, for example, in the Netherlands, and this is associated with manure management and the fact that farmers are less likely to fertilize their field on Sunday. Sunday is the best day in Europe, and you also have a regulation that prohibits the manure spreading on Sunday, for example, in Flanders, in Belgium, or in Britain, in France. This weekend effect has been confirmed from the ground. Looking at the surface ammonia concentration from the LML network in the Netherlands, all the stations also show present the minima on Sunday, Monday. And this even further confirmed looking at the seasonality of the weekend effect. We have two strong peaks in spring and late summer associated with the fertilization period. This weekend effect is up to 53% in the column, a decrease of 53% in the column, and up to 26% in the surface concentration. And this type of information is important to be taken into account in the air quality, in the atmospheric chemistry model, for example, to better assess the impact on air quality, for example. Satellite datasets are more and more used not only for spatiotemporal analysis, but also to assess new model development, or more recently to inverse emission at various scale. However, we can suffer from limitation. One of the first one is the fact that the current polar orbiting satellite measure ammonia at a fixed overpass time. While ammonia presents a strong head cycle, you have here the intraday variability. Here for all the stations of the LML network. The scientific return of the current mission is limited by that. Another limitation is on the spatial resolution. And the current satellite have a footprint of over 100 square kilometers. We need long-term averages to get this type of maps. And if I superimpose here the UPRTR register, you can see that we are missing a large part of the point sources. To tackle these two limitations, we have a lot of expectation for the geostationary satellite missions. For example, the IRS sounder, it will provide continuous coverage over Europe at a higher spatial resolution of 6 to 7 kilometers and at much higher temporal sampling with distribution every 30 minutes. And while we are waiting for IRS, there are already two instruments launched by the Chinese, and that these instruments can Asia 10 to 12 times per day. However, at a spatial resolution similar to the polar orbiting satellite of 16 and 12 kilometers. These are the first distribution of the DL cycle of ammonia reported by GEOS. And you can see, like for example, in April, in Punjab, we detect atmospheric column of ammonia, which are more than three times larger than what is measured during the night. Another mission that's it's also important to mention is the IRAS mission, and there is a new data set providing ammonia, new instrument providing ammonia data. And this is quite interesting because there will be also a series of instruments that will be launched at different overpass time, and they will therefore allow new insight in the intraday variability of ammonia at global scale. To further assess the future mission, we can use synthetic observation, and use model simulation at quite high spatial resolution. It's 400 by 700 square meter. And this is what will be shown, what will be seen by YASI new generation mission. This YASI NG has a similar sampling than YASI, but with an improved sensitivity and lower uncertainty. This will be launched in 2025. You have seen that we've been able to do a lot of science with such sampling. However, we miss also a lot of information. And as I have already said, this IRS mission will be really a game changer, providing this gapless coverage at higher spatial resolution every 30 minutes. But could we hope for even better instruments? We have worked for several years, and maybe say for a decade now, on the NITROSAT mission. This mission aims at measuring the main reactive nitrogen compound ammonia and NO2 at the landscape scale at a resolution of around 500 meters. Here you can see what NITROSAT would be able to see. This is the port of Antwerp. The aircraft measurements show several plumes, and this graph shows that only NITROSAT will be able to disentangle the different bond sources in comparison with the future planned mission. This is the same for the Pister site. NITROSAT will be the only instrument able to detect the plume emitted by that fertilizer. We also made the aircraft measurement in the Parma region, and here we have the agricultural emission. Again, we need this high spatial resolution to detect the smaller farming activities. Finally, this is what NITROSAT would see on this scientific observation. Unfortunately, NITROSAT has not been selected for the next phase, but the scientific committee has encouraged ESA to find other way to have this instrument launched. And if you have any contact or connection to help us to have this instrument in space, just please reach out. The current and future satellite mission will really be key to monitor the atmospheric changes following the nitrogen perturbation, and especially having in mind the forcing use of ammonia as energy carrier. And I leave you here with the ammonia maps from 2 days ago. And thank you very much for your attention.
Thank you very much, Mark.
Thank you. Sorry. Thank you very much, Martin. Questions from Martin? Yes.
Hello, Martin. So I started my PhD into this papers. So I grew up with reading your papers. It was very nice to meet you. So my question is like for showing the distribution of ammonia, do you use daytime or nighttime or you have an idea?
Up to now, we mainly exploit the daytime measurement because we have a better sensitivity. But as you can see here, the nighttime should be more exploited and are underexploited.
It's not, this plot you're showing is on nighttime.
This one on the left, you have the daytime, and on the right, you have the nighttime.
Okay. But this distribution temporal variation for the year, which you show for South Asia, it is decreasing for the latest years from 2021. One of the time series you've shown. Over South Asia, the time series, yes. Orange one is over India. So, why there is decline after 2022? Is there higher N2? What is the reason behind?
I don't know. It's maybe up to you to tell if you have, can use your model and tell us.
So I'm happy that the satellite product is not having averaging current data. So let's see in future how we can work it out.
Thank you.
But I'm very happy to say this in the variation, how it is going.
Thank you.
Thank you. So we have time for just two quick questions, which I'm going to take one after the other. So Luis and Mark. And so let's take those two questions at the same time, and then Mark, you can respond.
Hi, Indraprastha from Auditorium. Amazing presentation. I have so many questions, but just with one yesterday. We also attended to a great presentation by Magnus Reuter showing the evolution of nitrogen deposition in Europe according to modeling approaches. Do you think it would be possible to find a connection between those data or estimation on nitrogen deposition, particularly using compounds to the ammonia and the data set?
Let's just, before you answer that question, I just want to get Mark's question too, so we can get both questions, and then Mark will respond, and we'll have to move the rest of the questions.
Thank you, Martin. It's wonderful, great stuff. The first comment is you didn't get 90% funded. That's a great disappointment. It would only be a few tens of million euro. But you could make a business case in the fertilizer industry because it's manufacturing hundreds of billions worth of ammonia, and this would provide information to help them reduce that and improve their business performance on a financial case. That's the comment, worth investigating. The question is what you did not talk about, which is the limitations, the interaction with water, the cloud. Is the fingerprint of the absorption line so similar to water that you can never resolve that, or we're always going to be left with a world where we can only sample on sunny days and nights?
Thank you for your questions. This first, Lucy, I think that the best way now to proceed with the satellite data is to use them to constrain the ammonia in the gas phase, and that will help to constrain them the position as a constraint. And thank you, Mark, for your comments. I've noted the argument to help NITROSAT. Regarding your question, water is not really interfering much. It's mainly clouds. And yes, we will, I mean, if we need the radiation to reach the detector, and for that we will only be able to work on cloud-free spectra. And that cannot be changed. Sorry about that.
Thank you so much, Mark.
Thank you very much. Thank you.
Our next speaker is Vincent Indraprastha from Nigeria, who's going to be speaking. And John Percy is our valued colleague as an Africa director for INI as well, and he will be speaking to us about emerging megatrends, sustainable nitrogen management research in sub-Saharan Africa. Vincent, the floor is yours. Thank you so much.
Thank you very much, David, and good morning, everyone. We are happy to be here. So I'll be sharing a few thoughts of what we'll be doing in the continent of Africa. So as you have seen there, from Nigeria, I work at the institute there. So the outline presentation, I'll give a few overview and some things, recent advances about N in Africa. Now I'll talk about a few mega trends and how we concluding. In the continent of Africa, we have increasing population and it demands increase in food production, and nitrogen is low. It's a critical challenge in many of the ecosystems in the continent. To address the end problems, changes are needed through focal research on sustainable intensification, capacity development, and partnership. And key stakeholders, government, researchers, extension, and farmers are willing to take practical actions and share lessons for enhanced productivity, taking our destiny in our hands. It is Africa at a glance. By 2050, it will have the 12th highest population growth rates in the world, and it may likely double by 2050. And there are biophysical constraints that impinge on development that need to be addressed in Africa. The usage of fertilizer, especially nitrogen, is critical, and it's a challenge that is facing crop production in the continent. And one of the weak soil points in the continent is most of the research that are conducted by scientists are rarely used in decision making. They actually, why? Because they are not properly aligned with the needs of decision makers due to weak linkage between science and policy. So the scientists are working in silos and the policymakers don't see. So there's need for scientists to look at the policymakers and then bring science to policy. This is Africa. There are a lot of complex soil constraints. So you can see from the north to the east. So we have low soil organic matter, carbon exchange capacity is low. P, most of the soil thickly space, shallow depth, and so on and so forth. These are constraints. Of course, nitrogen is also embedded in these constraints. For over 2 decades, there is a project that is called Comprehensive Africa Agricultural Development Program, called CADAP, in Maputo 2003 and Malabo 2014. These are trajectories that are actually supposed to drive sustainable research, where also N is included in the continent. But of course, some countries have made progress, while some also are still lagging behind. In Africa also, we have land of sources. There are pockets by individual scientists and countries. But when we look at impact at scale, they are not adding up. And that is what we're trying to address. We have good scientists, but again, as I've said, most of the science are not actually tailored for policymakers. I think most time they are tailored for publications, for promotion. So it has some problems. Then, of course, limited funds, and then also we have weak institutions. So in the continent, we have very strong individuals, but our institutions are weak. But I think this one is being addressed. And it requires that we need to address some of these challenges at institutional level, at program level policy. So from local to the national, to regional, and to the whole continent. So we have to start at local. It means now where we are, then at national, then these are the different regions: North Africa, West Africa, Central Africa, East Africa, and Southern Africa. Then the whole continent. Let's look at a few things. This is fertilizer yield. If you compare Eastern Africa, Western Africa, North America, and Europe, you actually notice that why fertilizer application rate is increasing between that of nitrogen yield. This one is we are using maize as is low, so it means there's a disconnect. Then it is comparing Eastern Africa and Western Africa. We're also looking at fertilizer application rate and the yield of crops in Eastern Africa. It was reducing. Then once you apply more of nitrogen and NPK, you have increasing maize yield. This is typical agronomic nutrient use efficiency in the continent. So to my extreme right is nitrogen, why it is actually very low. It's about 6.5 kilogram N per kilogram of output. This is the nutrient balance scenario, between that of nitrogen in the continent. So you will see where we have low nutrient balance to a few, like part of East Africa, and you have very high, and then in Western Africa and part of Central Africa, the nutrient balances are low. So it means these are things that call for policy. Now, it's not all about negative balances and problems and constraints in the continent. These are emerging trends in agriculture sector in Africa. We need to look at it holistically because nitrogen cannot be isolated. So we are now moving toward digital agriculture, agricultural tech, smart farming and value chain innovations. And we have some good things coming from the continent, from FARA. FARA is called the Forum for Agricultural Research in Africa. It is a technical arm of the African Union in agriculture R&D. So in Africa, we have 7% of arable land, then we have 80% of fresh water, and more than 60% of population, they are young people, they are youth. We contribute 25% to GDP, then 70% are employed in agriculture. Then we have 50% urban food markets and share 10% of share agricultural exports. These good numbers are very important for us because we can actually pick nitrogen and each of the elements and see how they fit into the picture. Now, I want to now talk about a few mega trends. Basically, there are 8 of them but people are working in silos in this. But of course, the sub-regional organizations are trying to look at them holistically. So I will be talking about this one in detail soon. So we have, I've told you earlier, sustained economic growth. And nitrogen is actually key to this. So 6 of the world's 12 fastest growing countries are in Africa, Nigeria, South Africa, I think some part of East Africa also. So then we have rapid demographic shifts. I've told you earlier on. So you see the population. This, if you compare Africa and Asia and Latin America, Caribbean, Europe, North America, and Oceania, wide out of the developed countries and Latin America is declining. There's increasing population in Africa that needs to be felt, and research is actually needed to make this happen. Then in the continent also, we have a lot of smallholder farmers, and they scramble for farmland. So you can say Rwanda, Malawi, Kenya, Zambia, Ghana, and Tanzania. So, and this also has implications for nitrogen research. There is increasing demand for mechanization as a mega trend. And this one, of course, is going to be cost saving, but it needs to be tailored to the needs of the continent. Then, as a result, also we're having changing food markets. So you can see this is a typical farm. So there's a shift in diets, and some now are trying to consume organic food products due to pollution from nitrogen in the water bodies. So there's changing food markets, and research are being done by a lot of people in this area. Then the environmental trends in Africa due to climate change. These are areas that are actually most that have highest rate that's part of North Africa and some Sahel in West Africa. Then due to the climate change, land degradation, so the environmental trends, nitrogen component is also very important. Then Africa is trying to make sure that we harness industrial revolution. So the fourth industrial revolution technology that is based on strong innovation ecosystem, which includes skills, infrastructure regulations, and policies. They are key and germane. Then another aspect is financing agricultural research for development. This call for new partnerships, funding mechanisms, and framework for financing area for this. So these are the different projects and different initiatives by the African Union. There's a TAT, there's this is Science Agenda for Agriculture. These are bringing pocket of successes, but they need to be harnessed holistically. And there are some success stories from the continent that I need to talk about, and nitrogen is part of them. This, for the first time, the whole continent, in all the different countries, we have a uniform methodology for taking soil sample, even including for nitrogen. It was funded, it was a 10-year project funded by the Gates Foundation. So it's been domesticated. It's called the African Soil Information Service. So it's actually domesticated in the continent, and it's helping us so we can compare results and see how we are faring. Then again, the continent also, many of the countries, especially in West Africa and East Africa, are moving away from destructive wet chemistry to mid-infrared. And with this, you can analyze thousands of samples, including nitrogen samples, without using agrochemicals. So it's an emerging mega trend, and also it's advanced in research in the continent. For example, in my country, Nigeria, the one on the green, we after the 14,087 crop lands, Nigeria government for the next 5 years, and this also is being done in other countries, in Ghana, in Tanzania, in Ethiopia, in Senegal, to map the soils of each country, and from there we can cluster the one that has low nitrogen, the one that doesn't need much N. So it's being done at country level, and it's being supervised by FARA. I want to share a few synopses. In Africa, we need sustainable intensification. We have to develop capacities, the innovation ecosystems. These are very important for us. And then there's also the need for managing multi-stakeholder partnership. These trends, we believe, will bring science-led management to scale in the continent, and also help us to improve nitrogen knowledge of political decision makers. Now we are moved from the linear R&D model to the innovation system. So you can see the researchers, the extension, the marketer, the consumer, the agro-processors, and farmers. So when we develop any project, either at national or at regional levels, this innovation platform model is being used. So it means that we're able to move from the grassroots even to the top. Everybody is there, we can carry everybody along. This was the old picture of smallholder systems, including nitrogen in Africa. You can see all this thing, but now this is where we are moving. Gradually, we are getting there in good science, in profitable marketing, large scale, in mechanized farming, and so forth. So I want you to think about this, the take-home message, and also what you think you need for. I know that somebody told me yesterday from Europe, they want to do, there's a project they want to do in Africa on nitrogen. I was saying that we need to. So what is the status of N budget and N use efficiency in Africa? We have a lot of research that have been done on this,
but they are not yet properly customized. So I want you to think about it and area. Then the spatial trends of the nitrogen budget, nitrogen use efficiency in Africa. These are areas we need to think about. Capacity building along the entire knowledge transfer value chain is very important for us. I also need to think about it as your take-home message. Then we need to strengthen farming system research, development across biophysical and socioeconomic factors. We need to think about this. Then we want also to make sure that Africa, we can compare with the global north and also some countries in global south like India, like Japan, like China. So you think also about this. And this is embedded, our political leaders in the continent have an agenda called Agenda 2063, the Africa we want. And it's supposed to be driven by Africa through the African Union and the regional economic communities, self-reliance, progressive tracking, dedicated institutional governance. This is supposed to be the bedrock of both policy and technical research in the continent. I want to conclude with a few things. In May this year, there's going to be the Africa Fertilizer and Soil Health Summit. It's supposed to take place last year, November, but it was postponed. So it's going to take place in May in Nairobi. The whole of the continent is gathering, and also most people will be coming from many countries in the world. And we'll be looking at progressive perspectives on fertilizer manufacture, marketing, and productive use of soil health in Africa. Of course, nitrogen is going to form a part of this, but of course, you cannot take nitrogen out in silos. We'll be looking at how to implement priority action. There's a new drive called Soil Initiative for Africa and the Africa Fertilizer and Soil Health Action Plan. These are going to be addressed in its totality. Then strategies to foster Africa's resilience to global fertilizer crisis. Then addressing farmers' need for access to fertilizer, cost, availability, quality, and effectiveness. Then there's this one. There's a commission project that will be taking place at the presidential summit in May. It is called, our political leaders are insisting that we need to have a veritable soil information system in Africa, partnership, finance, and policy. So I'll be giving the keynote at the Presidential Summit in May in Nairobi. So you're welcome there. Then technology generation, extension, and capacity building for soil health and effective fertilizer use, including nitrogen, is key to us. These are the different partners in the continent that are supporting and actually helping us to do some of the things we are doing. The African Union, then we have the sub-regional organization like, I am from West Africa, and there we have CORAF, then you have ASARECA for East Africa, you have CADESA for Southern Africa, and AFAS for Extension. Then the civil society organization, then we're also working with the CG system and the Global Soil for partnership. I want you to look at this. There are a lot of challenges, but we believe challenges will always come, but overcoming them is a real challenge. We'll be hearing that too little nitrogen in Africa, but of course we are up to the task. Of course we have too little N, but we can actually customize it and make sure that we utilize it for our economic growth. So I want to thank you. Those are a few things I have to share.
Thank you very much, Vincent, for that whirlwind, multifaceted tour of the various aspects of the nitrogen challenge. And I think to thank you. Questions for Vincent? Yes.
Very much. If somebody gave a lot of money and said, pick up one topic.
What?
Want to focus on. Which one would they?
Can you repeat?
If somebody gave me, I'll put you a lot of money to tackle the nitrogen challenge in Africa, which would you think would be the lowest hanging fruit? What would be a focus? Maybe one theme out of the concept of this that is the highest impact.
Okay, thank you very much. Well, that's a very good question. I was telling them at a meeting, in the continent,
fertilizer issue is a bomb in Africa. So that is why you cannot actually take nitrogen alone. But of course, if you give, I have my way, we'll be actually looking at nitrogen use efficiency of crops. Very important. But of course, our political, like in my country for Nigeria, if subsidy is withdrawn from fertilizer, the government crumbles. People will not vote. So we have to look at the science. Also have to look at what our political decision makers are interested in. Of course, we do not downplay the science. So for me, we'll talk about nitrogen use efficiency, then, but I will not want to promote urea. Actually, we want to look at locally grown or locally manufactured organic nitrogen or a few of the inorganic for it. But of course, these are things that you cannot decide for yourself. So it has to be aligned to the national policies of the government of your country and also to what the African Union is doing. While we go for nitrogen use efficiency.
Thank you. Thank you, Susan. We have Tech for that.
Hi, Vincent. Very inspiring presentation. Thank you. You rightly mentioned in your key comments is that managing budgeting combat occupant continents is the way forward to understand what's going on, what is coming in, and then what's the level of using and developing. Do you have any suggestion on how we can enhance this bottom-up approach to developing these areas of that? Because a lot of these Google efforts are top-down and then they have to be close to the reality. So how can we go forward as the analysis research to work through?
Okay, thank you very much. I'll now, I think most projects that are conducted in the continent, there's a clause of open access. You know, on most, I have some data to show, but there are times you're not permitted. Like there's a project that is funded by OCP in Morocco, running into some millions of dollars. It's been a 5-year project, not only in Nigeria and many African countries, but there's a caveat. We cannot share the result until after 5 years. So there are times you have the data, but you also need to take permission from the donor. They want by gates, we don't have a problem with that. So we are working to address that. I think those are some of the things our political leaders need to talk about when we meet in Nairobi. It's very important for us. You have excellent scientists working in silos. They have their data, but at times they're not willing to share with you. But now in Nigeria, it has become a law because we have a project to map the whole soil and also customize nitrogen for cereals in northern Nigeria. So there's a database. I'm part of the committee, but it is entrusted with the Federal Ministry of Agriculture and Food Security. But Ethiopia has done excellently well in Africa. But of course, again, Ethiopia is not willing to share it. So we have those problems, but I think they can be solved.
Thank you. We have time for one more question with Mark.
Thank you very much, Vincent. You showed a very interesting map of Africa on soil degradation, and it showed that there was worse soil degradation in the east of Africa, and probably over there, two things. And but my question is, this map, which is very exciting, is why would it be worse in East Africa? That was it. Forward now. Well, I saw it when we went past. It was the soil degradation map, which is brown color, and it's very brown on the east of Africa, and less brown on the west. So the first question, is it published? Second question is, how was it derived? And the third question is, why did it exist?
Oh, this one?
Is it published? How was it done? And why did it exist?
Okay. Thank you very much, Mark. Some of the data were like this was gotten from ICRAF. Sorry, I deleted the other slide where I listed all the references. Well, some also were derived from Greek literature. Some are published, but there are some restrictions. So if this is not my, it wasn't my work. So what we did was just to aggregate from literature and also see. So this is what I can say. But I can talk, at least I can talk about Nigeria. I can talk about Ghana. I'm part of East Africa in Kenya, in Kisumu, because I was there. We did some work there and we published them, and those are the results we got. Hakim is not here. Doberman, I think he did a lot of work when he was with DG of Erie, and he also part of the absence. And one other thing I would say is I forgot to mention that we are solving some of these problems. Claire is here from France. There's a project called the Integrated Nitrogen Studies in Africa, where actually it is more of building capacity of African scientists. People go to Toulouse and some other European countries. And one of the key messages we are taking from the INSA project is collaboration and cooperation and data sharing. So that is one key what we learned from Europe. So that you don't close the space in Africa, you want to be like them. But of course, it's opening up a lot of visitors for us.
Thank you so much, Vincent. Please thank Vincent again. This is great. Right, we have come to the end of this plenary session, final keynote plenary session. We will give some thanks, a note of thanks to
Yeah, I would like to call both the speakers on stage to just get their token of appreciation from David Cat. Thank you, everyone. Before we take our tea break, I would like to extend a request to all the participants to join, to participate in a brief questionnaire, which is a survey conducted by University School of Law and Legal Studies at Guru Gobind Singh Indraprastha University. Your valuable input in helping them to understand and develop strategy to curb emission of small stakeholders, livestock farming activities. Participation in this survey is voluntary, but your contribution will be appreciated. Thank you so much for your kind participation. This session is over now, and a poster session is going on outside this hall. Kindly join me. And please submit your questionnaire at the registration links.
Hello, sir.
Hello?
Hello, sir.
Hello, can you hear me?
Yeah, audible, sir, audible. Thank you, sir. I can see you, sir.
Good.
Thank you.
Let me try to adjust the lighting here.
Okay, sir.
Hello, David? Hello? Eric?
Yes, I can hear you.
Eric, here is Lazareta.
It's very hard to hear you.
And we can hear you very well, Eric. Here, Luis Lazareta. I will be the co-chair of the session. Could you hear our questions or moderation or hardly? No? Can you hear us, Eric?
I can hear you, but it's very hard to understand what you're saying.
Okay. Okay.
Do you want me to share my screen and begin, or?
Yes, we will wait a bit because the session is about to start, but we are still waiting for the attendees, and we will let you know, okay?
Okay, perhaps if someone could speak directly into a microphone that's connected to Zoom, that would be better.
Okay.
So I can understand what you're saying. The person who was using the, oh, there you are.
Hi, Eric.
Yes, now I can, yes, now I can understand you.
Okay. We will start in about 5 minutes. Yeah, sure. Okay.
Okay. I will announce the basic announcement. Then I will handle you the session. After that,
I will present Eric.
yeah.
Okay.
So should I start?
Should we wait because everyone is still
5
coming?
minutes, I can.
5 minutes.
So
Eric, we are going to wait 5 minutes, more or less. It's okay for you?
Yes, that's fine.
And then the maximum length of the talk is 15 minutes, but people is sometimes even 12 in order to have time for questions. However, there is one talk that is not, won't be present, one presenter, therefore we have time for 15 minutes and maybe some questions, okay?
Okay, that's good.
Excellent.
we wait 3 minutes.
Okay. Excellent.
जब मैं बोलूंगी तब start करना. ऑनलाइन वाले सेशन में Okay. Okay.
We welcome you back in the highly anticipated international conference, the 9th International Nitrogen Conference, themed Balancing Global Change and Sustainability. This gathering serves as a convergence point for brilliant minds from around the world, fostering the exchange of ideas, inspiration, collaborative efforts to shape a sustainable future. We are thrilled to embark on this intellectual journey together. I would like to give instruction for all the oral presenter that there will be a 10-minute time for presentation, followed by 5 minutes for question answer. In this session, Ms. Asu Tyagi will be the rapporteur, and I would like to invite Dr. Louis Lasleta and Dr. Pil Jo Kim for co-chair the session. Now I hand over the mic to the co-chairs to proceed for the session. Thank you.
Hello, everyone, and welcome to this exciting session, the last session on cropping systems here in the conference. And it's a pleasure for me to introduce you Professor Eric Davidson from Maryland University. And he's giving us an interesting talk about greenhouse gas emissions in the corn maize rotation and the effect of water management on these emissions. Eric, if you agree, I will let you know when you are in 12 minutes, okay?
Okay.
And then you will have 3 extra minutes, and it's okay. And let me, okay, we can see your screen.
And is it in presentation mode currently?
Yes, it's in presentation mode. Therefore, when you want, the floor is yours.
Great, thank you. Well, I'm sorry I can't be there in person. I'm grateful for this opportunity to speak today. On behalf of my co-authors, Jake Hagedorn is the first author on this. This is largely from his dissertation, and a number of others who participated. I'm going to be talking about drainage water management in a part of the United States where you'll see in a moment that drainage is necessary for agriculture to occur in this region. The area that we've done our research is in the eastern shore of the state of Maryland in the United States. This entire peninsula that I'm showing here. I guess my trying to get my pointer to work, and it doesn't seem to be working.
So
there we go. Now I've got it.
Yes.
This part of this peninsula is naturally a wetland. Naturally, it was a forested wetland, but is dominated by agriculture now, in large part due to the fact that agricultural drainage ditches are widespread in the area. And that's necessary for agricultural machinery, tractors, and so forth to get into the land. One of the best management practices that's been introduced lately is to install these drainage water management systems at the end of each ditch. And as you can see here, it's basically a box through which the water flows. And this side diagram shows that we can add boards within this structure to raise the level of the water behind the structure. And then there's a V-notch weir in it through which we can use to measure flow. The boards are raised during the times of the year that the farmer does not need to get in with his tractor. And when the farmer does need access to the land, the boards are lowered so that the cropland is less wet and they're able to carry out their agricultural practices. The reason for doing this is that when the boards are raised, as shown here on the right, the water table is higher, and so the subsoil is wetter, has lower oxygen content, and therefore it's a good place for denitrification to occur, thus reducing the nitrate as it comes out of the small ditch into a bigger ditch, and reducing the nitrate that ends up eventually in the Chesapeake Bay, where it is a problem with algal blooms and water quality throughout the bay. So with this highly agricultural area, nitrate leaching and phosphate leaching is a very significant problem. The idea of using these drainage structures is it creates a subsoil where denitrification can occur, thus reducing much of the nitrate. Our concern, however, was that perhaps that the greater denitrification in the subsoil and perhaps even a wetter surface soil could result in more N2O and N2 losses, and perhaps even methane if it was sufficiently anaerobic. And so that's really what our question is about, is do we end up trading or swapping pollutants? We might be achieving reduction in nitrate, but at the cost of increasing greenhouse gases. And so that's really our question here. So this experiment was conducted on an active farm with the engagement of the farmer. And we created two areas, one with drainage or water management and one without. And you can see the ditches are in this aerial photograph are lined green with the green grasses. This was taken in the non-growing season so that you can see those ditches a little bit better. And within them, we had duplication of micrometeorological towers, of transects of chambers for measuring fluxes, with V-notch weirs at the end of each ditch. And we sampled the soils and also groundwater with using piezometers, and also sampled the ditch water. We analyzed soils and waters for N15. And the reason for doing that is that we took advantage of the fact that denitrification is a fractionating process. And this little cartoon describes how denitrifying bacteria fractionate by selecting for the lighter isotopes of both nitrogen and oxygen, leaving behind forms that have that are enriched in the heavier isotopes of both nitrogen and oxygen. And there's considerable literature on using this as an indicator of denitrification based on the work of Carol Kendall from, I don't know, 15 or 20 years ago, that we can look at certain sources of nitrogen tend to have a certain range of N15 and O18. And as denitrification occurs, they both become more enriched over time. And that at least gives a qualitative indication of denitrification. That's one of the things we're trying to do, and we'll also make a quantitative indication. So here again is that map that I showed you before. And ideally, our hypothesis anyway, is that as we sample from the surface soils to the deep soil, to the water that's in the piezometers in the field, to the water that's in the piezometers right next to the ditch, and the ditch water, this is a pathway. It may not be the only pathway, but it's one of the pathways that waters would be moving and the nitrate would be moving. And in theory, as it moves along that idealized pathway, it ought to become more enriched in both N15 and O18. On the right is our data. On the left is that hypothesized diagram, and you can see that in general we have the trend that we'd predicted. Although interestingly, it's shifted a little bit to the left, and the reason for that is that we're actually seeing the combined signal of nitrification and denitrification, because nitrification would select for creating nitrate that is somewhat lighter in N15, but not necessarily O18. So the N15 is shifted a little bit lighter than we would have expected based on if it had been denitrification only causing isotopic fractionation. But along this gradient from the surface soils to the ditch, we do see this trend of increasing enrichment of both N15 and O18. That supports our hypothesis of that continuum of denitrification, but with an effect of nitrification as well. We also used a mass balance. So we know from working with the farmer measured and it reported to us the amount of fertilizer in both the drainage water management areas and the non-drainage water management areas. And we can take estimates of atmospheric input from nearby weather stations. We also collected them ourselves. We measured the nitrate in the irrigation water used by the farmer. We measured the hydrologic export using those weirs that I showed you at the end of each drainage ditch. The farmer measured for us the amount of the total amount of crop, the yield, and we measured nitrogen concentration of that crop. And by difference, we have estimated what the total gaseous export would be. And you can see here that the main differences, because the farmer treated all of the plots identically, the main difference is that in the drainage water management, there was less hydrologic export of nitrogen, predominantly all as nitrate. And therefore, by mass balance, we calculate that there is more gaseous export. And a very large sum, in fact, of the over 200 kilograms per hectare applied by the farmer, nearly 100 we're calculating being lost by gaseous export. And so you can see the gaseous export is the second largest export, but not significantly different by treatment, given the errors in the assumptions of mass balance. And so this is a common problem we have with mass balance, because we're estimating the gaseous export by difference. You end up combining all of the error terms from all of the other measurements. And so although there does appear to be a difference, if you look at our error terms using a Monte Carlo approach, those means are not statistically significantly different. However, our N15 nevertheless gives us further information about this. So if we also solve a mass balance for N15, we have to make a few assumptions and some measurements of the N15 from fertilizer and atmospheric input. We've measured it in the irrigation water and the hydrologic export. We made those measurements. We've also measured it in the crop. And so we can, through this same mass balance approach, come up with what the N15 of the gaseous export must have been. And comparing that to the N15 of the bulk soil, we can calculate a discrimination factor, which is in the range that one would anticipate for discrimination for denitrification. So that is the range reported in the literature is between 13 and 35 per mil, and we're seeing ranges towards the lower values towards the lower end of that range, but nevertheless within the range one would expect for fractionation for denitrification. Now, that is the total gaseous loss, but we also were able to measure N2 and N2O in the groundwater itself, and using N2O using gas chromatograph, N2 using membrane inlet mass spectrometry. And as you can see here, the N2O dissolved in the groundwater as it was reaching the ditch was very, very low. And so it looks like our end product in the groundwater is primarily N2, and indeed the excess N2 higher, the N2 concentrations that are in excess of what would be in equilibrium with the atmosphere are quite significant. There's a good deal of variation among our 4 ditches.
3 minutes, Eric. Thank you.
Okay. So if we put that together in a mass balance, we have the inputs from fertilizer, atmosphere, irrigation, and we've measured the output in the crops, the hydrologic output, and the total gaseous output. And we can attribute the total into the dissolved N2 and the dissolved N2O, as I just showed you in the last slide, in the irrigation water leaving the ditch or going into the ditch. And we've also measured the N2O emissions both by chamber measurements and by micrometeorological towers. And again, by difference, then we attribute most of that gaseous export to N2. Now, we've had to make some assumptions about other measurements that we haven't made. We're going to be returning back to this to look at what possibility could be for a significant ammonia emissions, for example. It's interesting that our N2, the ratio of N2 to N2 plus N2O aligns pretty well with the literature of the N2O total being along between 5 and 10%. And the denitrification as a percentage of N inputs also aligns with the literature of being somewhere in the 30 to 40% range. Although it's a large number because in this particular field, it's pretty high fertilization rate. So with our conclusions, the nitrate isotopes indicated first qualitative evidence of co-occurrence of nitrification and denitrification. The mass balance determined that gaseous N export is a substantial fraction of the outputs, and it's dominated by N2. We didn't see a definitive statistical impact of drainage water management on gaseous N export, particularly not on N2O. And therefore, that's good news that we can apply this particular best management practice to reduce nitrate leaching and not have the counteracting effect necessarily of increased N2O and methane emissions. I did not show the methane emissions here, but they were negligible. And the N15 isotopes in the mass balance corroborates this denitrification inference. So thank you for your attention. And if there's any time, I'd be happy to take some questions.
Thank you, Eric, for the great talk. Is there any question in the room? I have, Eric, some questions. I wonder, first of all the N2O emissions that you estimated are associated to denitrification, but not to nitrification also?
Well, what we did is that we can't necessarily say that there aren't any that are coming from nitrification. Of course, that's possible. What we did was we estimated, well, we measured N2O emissions from the field using chambers and also using towers. So we have estimates of what the N2O is. What we're doing in terms of mass balance is saying, what is the total gaseous loss? And then looking at the N15 to say, it's clearly a signature showing that there's very significant denitrification occurring. And also very high ratios of N2 to N2O. And so one deduces from that that denitrification is the dominant source. It certainly doesn't rule out nitrification as contributing to N2O as well.
Okay, thank you. There is any other question? And if no, I have a last question. Therefore, you can conclude that this would be a good way to remove nitrogen from the water without a big impact on N2O. This is your main conclusion, is true?
Yes, this is our conclusion for at least for this particular farm and this particular situation. You know, to look at it more broadly as to whether this type of drainage water management would be effective under other field conditions. Obviously, that would need to be verified in other places, but it's very worthwhile, I think, or very reassuring, I should say, that in this particular region where this best management practice is being promoted, that it would be beneficial in terms of the net benefit to the environment.
Okay, thank you very much, Eric. We have to move on.
Okay, thank you.
Thank you. Bye.
Bye-bye.
Okay, the next speaker is Joao Serra. Joao now working in Denmark, it's true? Not, okay, sorry.
Joao is from the School of Agronomy of Lisbon, and he has prepared a great work on searching for the nitrogen content in the irrigation water. He has good results to share with us. You have about, we can say, 13 minutes, and I will let you know in 30 minutes.
I will
okay?
try to do to do it less.
Okay, welcome.
Yeah, exactly. Five. Thanks. So good morning all. Today I'm going to present you the nitrogen in irrigation water. This was already published, but I thought being in India, which is as of today, I think 2 days ago it came out a new paper about like irrigation data sets at high spatial resolution, and apparently India has the largest irrigated croplands in the world. So being in India, which also has nitrogen problems, I thought it would make sense to stress out again like the importance of irrigation water in agricultural systems, specifically in irrigated systems. I'm just going to provide an overview. If you want to further explore the material, you can go here, specifically the methods. So we already know there's a large problematic around nitrogen pollution to surface and groundwater bodies, right? And you might think like, so what's the deal with irrigation, right? If we think about it for a second, I think it's pretty obvious that irrigation must come from somewhere, right? So if you have nitrate contaminated water bodies, and if you're taking the irrigation from there, obviously the irrigation will transport additional additional amounts of nitrates, which is often not accounted, nor by farmers, often not by scientists, although things are changing, fortunately, and specifically not by policymakers. Now specifically in European policies, it seems like there's a missing link, not the missing link, but certainly a missing link between the water cycle and the nitrogen cycle through irrigation. So this additional nitrogen from irrigation is not accounted for in the agri-environmental indicators that are used in the Common Agricultural Policy in Europe, which is sort of like a way for countries to benchmark their performance to see whether improvements are being made or not. So what I propose to do, me and my co-authors from across Europe, is that we wanted to understand whether this input is relevant or not. We wanted also to further explore whether if there's a significant effect, whether it's local or more regional or even national. We also wanted to understand like the impact of not including these new inputs in the agri-environmental indicators like the nitrogen surplus or the nitrogen use efficiency. So conceptually, this is rather simple, right? You just have to know the irrigation amounts you're applying to your fields and the concentrations from whichever water source you're using. Of course, if you want to go a step further, things are a bit more complex, but I think because we wanted to get like a prima facie evidence that this is relevant or not, we try to simplify a bit the methodology. So we only calculated the irrigation requirements for approximately 40 crops, and we predicted the concentrations in groundwater and surface water in Europe. These are papers, if you want to further explore, that we use in the methodology. So I'm just going to provide an overview, okay? If you're not aware, in Europe, you have a quite, how can I put it, a quite marked variation in terms of the agricultural systems, right? Specifically in Mediterranean Europe, where the climate is a bit more dry, you often need irrigation to boost crop production. So evidently that most of the irrigation withdrawals occur in the Mediterranean climates, specifically Spain, Greece, and Italy. There's also obviously like a latitude gradient. So the further south you go, the more irrigation you need. Here you can see the spatial variation of the irrigation requirements. It's average for 10 years. Because at this scale, it's often a bit hard to, right? Oh, sorry. Because at this scale, it's often hard to understand whether your predictions are accurate or not. We simply compared our predictions with other global hydrological models, and we can see a relatively good comparison. The values sort of matched, which is not necessarily it means that it's accurate, but I think it's a positive sign. Is the nitrate concentrations in groundwater. In my next presentation, I'm going to further explore this a bit more. There's several limitations about the resolution used, which is 10 by 10 kilometers. As you can see the local effects, but nonetheless, it's useful for us to gain an understanding of what's going on in the groundwater across Europe. You can see many scattered hotspots across Europe. I would like to highlight in southern Spain, in the Guadalquivir basin, a large hotspots where it's also a very intensively irrigated area. You can see the patterns here, the temporal patterns, to understand what's going on. So essentially, we wanted to understand which is the main driver regionally for the irrigation, the nitrogen inputs from irrigation. We achieved a relatively good performance when predicting the nitrate concentration in groundwater. There's still much to be done, mainly because data requirements are not being fulfilled, but it's also a positive sign that we are doing something good, I guess. So we calculated nitrogen in irrigation water sources, right? We found not a increasing trend, although it was not statistically significant. And we could see an interesting effect that the majority of the nitrogen input from irrigation water was concentrated in approximately only 13% of the study area, which concerns the Mediterranean climates. Approximately 70%, 70% to be more specific, bit more specific. If you look at the plot D in the variation for the different countries, we can see a really curious effect about the variation of these inputs across the countries. We can see that on average, I wouldn't say it's not significant, but it's sort of small, right? Like in Greece, which achieved the largest average, it's about approximately 25 kilograms of nitrogen per hectare. But if we look at the dispersion, we can see some values reaching upwards to 400 kilograms of nitrogen per hectare, which is a lot, and often even higher than the amount of fertilizers being applied. Here we can see the spatial variation, the average spatial variation. The black dots, which are very small here, correspond to to cells that attained statistically significant trends. Some values in Southern Europe were really high, which was sort of surprising. Like if this input can be so substantial, why are most farmers not being aware of this, right? We also calculated the uncertainty, which was 25%. I think it's acceptable given the scale that we used here. We can see the trends, like we can see that in most of France and Spain, it's actually increasing. Whether it's due to irrigation requirements or due to the increasing in the nitrate concentrations in the water sources, it varies quite a lot, right? In the Mediterranean climate, usually it's both high irrigation requirements and nitrate contaminated water sources, both the main drivers. In Northern Europe, we found that it's mostly high nitrate concentrations in groundwater. In India, recently the image team published a study in India, and they roughly quantified this input in India to be almost 2 teragrams of nitrogen per hectare, which is approximately 25 kilograms of hectare per year at the national level, which is a lot. They also made a comparison with the total nitrogen inputs, and they amounted to almost 8%. And if you think about it, this means that quite a lot of money is being wasted in fertilizers. And of course, there's quite a lot of nitrogen pollution as well, because you're not accounting for these inputs. We use the integrated model to benchmark the impacts of irrigation in terms of the agri-environmental indicators. This was made at the nursery scale, which is a regional scale, and it only accounts for total cropland, not irrigated cropland. So the results here are, I would say, probably severely underestimated in some regions, and they are more a function of the percentage of irrigated cropland in the regions. But you can see that the impact on the NUE, so by not accounting for irrigation on the nitrogen use efficiency, sometimes you lose upwards of 30%, but in fact, this value should be much higher. In fact, in Portugal, we estimate that sometimes this reaches up to 80%. So you are overestimating NUE by 80%. Conversely, if you are overestimating the nitrogen use efficiency, you are also underestimating the magnitude of nitrogen pollution by not accounting for this. So I would say, like, our data shows that agri-environmental policies, more so in Mediterranean countries, are underestimated the nitrogen use, are overestimating the NUE and underestimating nitrogen pollution. And we can see here that the effects are mainly local, right? Because the effects at national scale are rather small. Like Greece, which is a country where this input is really, really substantial, the impact is less than 3%, which is rather small. But if we go to this map, we can see that sometimes it's almost 50%, in fact. There's still much to be done about this, right? I think in the future we're going to employ more detailed methodology to explore more locally these effects, right? But so far, I think that the results have been really promising. There are large gaps yet on statistics, mainly. Like if you go to FAO stat, you barely see anything about irrigated land. New data sets are coming in, which is always nice. We have to employ a better water balance model, a more detailed one, maybe a process based in the future. And also there's a particularity about the nitrogen dynamics and the boundaries, both in time and space, that we define, right? Because indicators are collected at the annual step, but essentially the irrigation dynamics are monthly or even daily. So we might be double accounting for some of this nitrogen, depending on the residence time and also on the spatial scale. But I won't go into depth about it. You can read it in the paper. I think it's easier. And basically, that's it. Thank you for allowing me to be here. It's a pleasure.
Thank you, Joao. We have time for some questions. Yeah.
I was curious about the high concentrations in southern Spain. Could you talk a little bit about what may be going on there? Is that, you know, theological nitrate in those waters, or what may be going on?
We basically applied a predictive model. So we collected the monitoring stations across Europe, and we developed predictive modeling using random forests. So that directly predicts the nitrate concentration in groundwater. So as you maybe know, it's a black box, so we don't really know what the main processes behind the high nitrate concentrations. But I think the accuracy in Spain is relatively high. So I think we are reflecting reality here. I don't know if this answers your question.
was thinking that there will be more, maybe in the Catalonia area where there's more animal production than the southern part, so that's kind of caught my attention.
We developed a new model, so with a better spatial resolution, and there you can find that specific hotspot in the Ebro Basin. You can really see the hotspot that you can't see here because of it's diluted in the cell size. You know, it's 10 by 10, and you lose a lot of detail about the spatial variation of the nitrate concentrations. I have my next presentation will be specifically about it, so maybe you can see it there.
If I can answer, and I ask my Spanish colleague to confirm what I'm saying is right. But the region, the red region, this is for you. Sorry. The red spot region in south of Spain is roughly overlapping with the region where they have intensive horticulture of production. So that may be actually the logical reason for having how the region might get done.
And also you have really low residence times there. So the nitrate dynamics are very fast.
Thank you. We have time for last question. Yeah.
I'm a geneticist, so I don't really follow all this. I'm not at rice, right? My understanding of most of the rice production in Europe is fed by rivers.
Rice production.
Yeah. Yeah. So irrigated rivers. You don't include rivers.
I include rivers, but rivers are tricky, you know, because we are using an annual time step, and usually the dynamics are much faster on rivers. So you would need more data and higher resolution. And for that, we had to assume the averages per basin. So you lose a lot of detail. But the concentrations, they are also lower than in groundwater. So the input, it's much smaller. It's sort of, in Europe, it's sort of 30%. So I would say most of the impact is on groundwater fed crops, and rice is not one of them. Thank you.
Okay, thank you, Joao. We are welcoming Castilla China from the National Institute of Environmental Studies in Japan, and he's going to present an interesting presentation on a meta-analysis about different options to reduce fertilizer application in Japan. And Kazuya, you have about 30 minutes. I will let you know when you are ready in 30 minutes. Okay?
Yeah.
Thank you.
Is it pointer? Oh, sorry. Okay. Luis, thank you for introduction. I'm Kazunishina from Japan. Today I talk about the national new policy for the agriculture. At first, I'd like to introduce our new policy for the strategy for the sustainable food system called Midori. Midori means green in English. Midori Act have started since 2022, and this act aims to achieve the 30% reduction of the chemical fertilizer use and increase organic farming up to the 25% of the farmland in Japan. It is very similar strategy with European farm-to-fork strategy. Another background, this is the recent nitrogen fertilizer prices in Japan. And as you can see, the price have been rapidly going up, and in the maximum 2.5 times higher than before the 2020. It keeps still high, and now 1 time higher than before the 2020. So now farmers also want to reduce fertilizer use because of the cost. So now it is very good timing. Governments and farmers see the same direction to reduce the fertilizer. And this is the background in the from the view to the global context. Right figure shows the relationship between the GDP and the nitrogen fertilizer input intensity in the cropland, and the color indicates the global regions. And here, KAJ indicates Korea and Japan. Yeah, we have the second largest nitrogen fertilizer input intensity. And also the right figure shows the Japanese average nitrogen use efficiency. For the crop, it is about 30%. As you can see, it is less than the global average. So it means we have a large room to reduce nitrogen fertilizer. Okay, so but there is no scientific evidence for the middle targets, 30% reduction. So in this study, we aim to validate the feasibility of the middle targets. And then we quantify the consequence of the middle target on nitrogen waste. So in this study, we used a meta-analysis. Actually, there is a large gap between the national target and each agriculture management. But fortunately, we have so many existing fertilizer reduction experiments, and from the large data set, we can validate the feasibility of average reduction potential from the large data sets. It is major assumption of this study. Okay, so let's move on to the material methods. I'd like to skip in detail, but we use not only scientific paper, but also come from the reports from the local governmental agriculture experimental station. So no scientific papers. And we categorized reduction method, 4 types of the reduction method in the database. One is a simple fertilizer reduction. It means the just reduction without the change of the fertilizer type. And the next one is a functional fertilizer. It means the replacement of normal synthetic fertilizer by functional fertilizer. For example, slow release fertilizer. And third one and the fourth one are the organic fertilizers. Total or partial synthetic nitrogen fertilizer is replaced by the organic materials. Anyway, it is a summary of our database, and the right figure shows the geographical distribution of the records of each treatment, and the right table shows the records in each reduction method and each crop types. Totally, we compiled about 1,900 records in the database. Okay, so first we define the reduction rates in a synthetic nitrogen fertilizer. This is the definition. And the right figure shows the relationship between synthetic nitrogen fertilizer rates in a control plots and the reduction rates. I'd like to say there are no correlation. So very independent data set. Okay. And next, we analyze this database by using the statistical model. The first one is a very simple model. This is a linear regression, and Y indicates the yield response ratio, treatment by control, and X indicates a reduction rate of the synthetic nitrogen fertilizer. And the second model is also a very simple model, segmented linear model. It is also called the piecewise regression. And this model estimates a breakpoint. A breakpoint divided two lines for the regression. I think you can understand in our results. So this is our main result. X-axis indicates a reduction rate of synthetic nitrogen fertilizer, and the Y-axis is a yield response ratio. If one indicates the same between the control and the reduction treatments. So red line indicated the estimated segmented line, and here is a breakpoint for two lines. And as you can see, until the breakpoint, slope is very low, small, and it is very in this area no significant trend, and it means we can reduce synthetic nitrogen fertilizer without yield loss until this point. Okay, so our estimated breakpoint is higher than our target. So we can say, yes, middle target is feasible. Okay. So we can give the scientific evidence to the national targets. It's very good for us. So anyway, next step, we divided this data set to the each reduction methods. And the lines are same, segmented lines. Unfortunately, the estimated breakpoint are less than the middle target in each treatment, but in the organic fertilizer and the functional fertilizer, slope are very small and less sensitive to the reduction rate of the synthetic nitrogen fertilizer. So it is possible to use functional fertilizer and the organic fertilizer to reduce synthetic nitrogen fertilizer. Anyway, actually, this is only considered the reduction of synthetic nitrogen fertilizer. In the organic fertilizers, it is nitrogen input is not how to say. Sorry, we have to consider the total nitrogen input in the organic fertilizer treatment. So this is relative nitrogen input to the control, sometimes over than 100% because of the organic fertilizer use. And the y-axis is the same response ratio. And here we further divided by the how many years organic fertilizer application, and single, multi-years, and more long term. We can say in the long term, more stable for the yield response ratio. Okay. So I'd like to skip. Finally, I'd like to evaluate the consequence of the middle target. So this is the current nitrogen flow, cropland nitrogen flow in Japan, and the left hand are the inputs, and the right hand and the harvested crop, the nitrogen amount of the harvest crop. And as you can see, the upper arrows indicates the atmospheric emission, and the lower arrow indicates a leaching and recycling. Okay. And as you can see, the nitrogen use efficiency is very low in Japan. But another important thing is in Japan, organic fertilizer, now already organic fertilizer use is more than the amount of synthetic nitrogen fertilizer. So it means the less the small potential by, how to say it, I'm sorry. It is reduction potential by the synthetic nitrogen fertilizer is very small to the nitrogen waste. So finally, I evaluated this by the very simple scenario. One is replace synthetic nitrogen fertilizer reduction by the organic fertilizer, 100%. The second one is a simple reduction in synthetic nitrogen fertilizer. Left figure shows the inputs to nitrogen inputs, national nitrogen inputs, and the middle figure shows the output of the nitrogen gases and leaching. As you can see, the first, this scenario emit more nitrogen waste because of the ammonia emit more compared to the synthetic nitrogen fertilizer. Okay, so I think it's not surprising result for nitrogen community, but the policymakers, not for the policymakers, actually sometimes they don't recognize such problem. Okay, so that is my presentation. Thank you very much.
Thank you for your presentation. This is Mr. here.
Excuse me.
The zero question, because that would be applicable on farm management practice. And would that slope be
Thank you very much. Sorry, could you? No, this one. I see, yes. Actually, yeah, thank you very much. Thank you for very important question. Actually, in the organic fertilizer, zero means no nitrogen. Actually, organic fertilizer inputs should be counted. But yeah, here, this is a zero. Yes, it has a little bit bias. So I'd like to evaluate without zero values. Thank you very much.
Is it enough? You understand? Okay, so let me ask more. And is there application more? Okay. No. Okay, thank you so much. Thank you, Kazuya. Not here in Europe, I have this farm to focus strategy. It's a similar objective of, in this case, it's 20% reduction of fertilizer applications. In the case of Mallory, is 30%. And this strategy in Europe is quite ambitious because there is also a second target that is a reduction of 50% of the losses. While I find that this can be very difficult, only using 20% synthetic fertilizer, of what kind of things should we do to reduce 50% of losses? I wonder if Madori strategy also includes not only a target of reduction, 30%, but also a target of reduction of losses in the environment.
Yes, thank you very much. We do, it is very difficult target, 50% reduction. For, as you know, the Kunming Montreal Global Biodiversity Framework, it says halving excess nitrogen loss. But yeah, but still we have a large room to improve the nitrogen use efficiency. So we need more wise management in agriculture sector. But yeah, halving is very difficult. Yeah.
Okay, thank you so much. Obviously,
thank you.
Moving forward to the future, like, okay.
This one? Yeah. This one? Maybe.
Thank you, sir. First of all, I would like to thank the organizers for giving me this opportunity. Good afternoon to you all. My topic is assessment of genotypic variability and improving nitrogen use efficiency in irrigated rice. I need not emphasize the importance of nitrogen here because it has been under discussion for the past 2 days, and we all know that nitrogen is the most essential element that is required in large quantities, but its use efficiency is very low, and there is a need to improve nitrogen use efficiency. Varieties differ in their ability to absorb and utilize the nutrients, and genotypic variation in nitrogen use efficiency in rice was reported by several researchers long back. And the nitrogen use efficiency is exactly defined as the maximum economical yield produced per unit of nitrogen applied, absorbed, or utilized by the plant to produce grain and straw. And the genotypes which produce higher grain yield at low level of nitrogen and also respond well to added nitrogen are the most desirable ones, and hence the existing nitrogen use efficiency in popular varieties need to be very well understood for further improvement in the nitrogen use efficiency, along with other approaches like molecular approaches, agronomic, resource or input management approaches. With this background, this study was undertaken with these objectives: evaluate the nitrogen use efficiency of existing popular varieties and to identify the efficient genotypes for their responsiveness and also the use of soil and applied nitrogen, and to evaluate the urease inhibitors in comparison with imported urea at greater levels of nitrogen, and to test these urease inhibitors at reduced levels of nitrogen compared to 100% NCU, and also to study the relationship between nitrogen use efficiency and seedling vigor. This is the real view of the experimental side. And coming to the experimental details, this study goes like this in 4 experiments. The first one is 21 genotypes were subjected to 2 levels of nitrogen without external N application and with 100 kg N application. And in the experiment 2, 2 urease inhibitors were along with the NCU were subjected to graded levels of nitrogen here. This NVPT is the commercial and chemical urease inhibitor, and allicin is the plant-based one. Plant-based allicin is an organosulfur compound extracted from the garlic oil that has urease inhibition properties. And these were compared along with NCU at graded levels of nitrogen. And in third experiment, these urease inhibitors were tested at lower levels, that is at 80 kg N only, along with 100 kg of imported urea. And the fourth experiment was germination and seedling vigor study in pods. Let us see the results one by one. And the first experiment, this is grain yield data of 21 genotypes at N0 and N100 in both seasons, wet as well as dry seasons. Here some genotypes responded well performed well at N0 condition, some responded well to at N100, and some performed well at both levels. And based on this granular data, we grouped all these genotypes into 4 groups. The first group is high yielders at N0, but less responsive to added nitrogen. This is considered as efficient group, and this group can directly go to the resource poor farmers who cannot afford to apply fertilizers. The second one is high yielders at both levels of nitrogen. These are considered as efficient as well as responsive, and these genotypes are adaptable to the wide range of N environments. And the third one is responsive group. Though they are not very high yielders at N0, but they responded well to N100. And this group is responsive, and breeders can use in their breeding program this group of varieties. These are some of the efficient genotypes at N0 level. And we calculated important nitrogen use efficiency indices also for these genotypes and ranked them into 1 to 21. And these are the top rankers, top 6 rankers, and these are bottom 3 rankers. Here, no single genotypes recorded the maximum values of all the efficiency indices. So we have to take the mean values and give them the rank as per their mean ranks. Coming to the second experiment, this is grain yield with urease inhibitors at greater levels of nitrogen. And this is grain yield data at greater levels of nitrogen. Here you can see, though grain yield was maximum at 100 kg, there was no significant difference between 75 and 100 kg. And with regard to the urease inhibitors, these 2 urease inhibitors performed better than the neem-coated urea by 17-25%. This is west season data. And this is dry season data, and the trend is same in dry season also, showing no significant difference at 75 and 100, and with higher yields with these urease inhibitors. These are the pictures at 100 and 75 kg. Both are looking same without any significant difference. And the third experiment is testing of these urease inhibitors at reduced levels. As a confirmatory study, we have done this. These 2 were given at 80 kg only, and NCU was given at 100 kg nitrogen. And these urease inhibitors with 20% reduction in nitrogen recorded almost same or marginally higher yield by 7 to 12% over 100% neem-coated urea. And these are the pictures with 100 kg neem-coated urea and 80 kg of urease inhibitors, NBPT and allicin-coated urea. And we estimated the urease activity also at 5 times during the crop growth period. So here you can see these are the mean values. After basal first split, before splits, after first split, before second and after second split. These are the mean values. And here urease activity was found less where urease inhibitors were added compared to NCU treatment. And this is indicating that slow and gradual release of the nitrogen over a period of time throughout the crop growth. And this is the final and fourth experiment, germinated seedling vigor experiment. Initially, 21 genotypes were subjected to this seedling vigor test. And from these 21 genotypes, we have selected 9 genotypes that included both high and low NUE varieties and subjected them to confirmatory studies in pots. This is the seedling vigor of high and low NUE varieties. And seedling vigor 1 is based on total length of the seedlings, and vigor 2 is based on the total dry weight of the seedlings. Here, interestingly, high NUE varieties recorded high seedling vigor and low NUE varieties recorded low seedling vigor. Thus, we can understand that seedling vigor also contributes to high nitrogen use efficiency. And the broad conclusions that can be drawn from this study are 20 to 25% of nitrogen can be saved with improved genotypes and urease inhibitors. And high nitrogen use efficiency is also associated with high root and shoot parameters and also high seedling vigor. Thank you all.
Thank you very much. I think we have time for some questions. In the room. Yeah. Hello. Do you think because you are having varieties of different nitrogen deficiency, so do you think whether these varieties have equally some some influence on the different laws, mechanisms of nitrogen?
Different loss.
Yeah.
Loss, and we did not estimate any losses from this. I mean, we have to test these genotypes for various gaseous losses and all nitrification, but we did not attempt to that. But in another study, one of my colleagues is doing with the different genotypes, gaseous loss estimation, and genotypes differ in their gaseous losses also. That was there.
Thank you. Director?
Sir.
Yeah, Tom, this is an obvious question. Could you comment a little bit on your choice of the genotypes that you chose? And is there any pattern in the ones that you identify as superior? Is there anything similar about their origin? Yeah.
The basis is high yielding varieties which were released over during recent period of time, like that I have selected. This is the latest data. I started from 2010 and 11. Every year I was taking 15 genotypes pertaining to the release of that particular period, and then I was testing like that. Like that, so far I have tested around 90 genotypes. And now what I am planning is every year we will be identifying some efficient 3 to 4, and all of them together in a specific experiment. Again, I wanted to do for all these characters to come to a final conclusion.
Okay. Thank you very much.
Thank you all.
Okay, we are giving the floor to Alison Miguel from the Environmental Defense Foundation. She is giving us a talk with real examples and real farms here in India and the United States about reduction and management of nitrogen. You have 30 minutes. Okay.
Thank you, and thank you everyone for coming. I want to start by acknowledging my co-authors, others on our science team at Environmental Defense Fund, as well as some who are based here in India and doing implementation work as well as science. So Environmental Defense Fund is a global nonprofit organization. We have over 1,000 staff in more than 30 countries. We put science and economics at the base of our environmental solutions, and we collaborate with university and other partners in science to bring that best available science into application in policy and supply chain solutions and other opportunities that we can identify. So I'm a senior scientist on the Climate Smart Agriculture team. I guess I have to click instead of press the down arrow. Oh, that's what I tried. All right, so I'm not going to read all of this because this is the theme of the week, and you've all heard these things about fertilizer nitrogen being important, and we have low efficiency, but we really want to think about the wasted effort, the wasted money spent, as well as the direct costs to governments where, for example, the government of India spends approximately $20 billion US to subsidize the cost of fertilizers. And then global nitrogen balance is exceeding our planetary boundary. And so this is where nitrogen balance being inputs minus what's harvested as the crop, and this is the theme of my work, where we are going to talk about the cropland nitrogen balance, where we've heard a lot of top-down work on nitrogen balance. What we are thinking about is from the bottom up at a field scale, but also scaling up. So the average cropland nitrogen balance that we would want to have to keep within planetary boundaries has been suggested to be about 40 kilograms of nitrogen per hectare. And then we've seen other safe zone kind of estimates. For example, the European Nitrogen Expert Panel estimated a maximum nitrogen balance that we wouldn't want to go beyond 80 kilograms on a given field. So we have all these ideas, these big picture. We should be shifting nitrogen from one place to another. We need to reduce it. And we know this problem. And why are the solutions so challenging? And I guess I'm going to start by saying that for farmers, most aspects of their production are not necessarily within their own hands. It's not just that we need to convince farmers to make changes. There are other things that are going on, reasons why they're making the choices they're making. Sometimes the idea of more is better stems not from convenience necessarily, but from desperation in trying to get the best yields possible. We've got extension efforts, arguably in some places better funded than others. Investments by government in conservation are often low. They compete with yield contests, we compete with subsidies, advice being tied to sales so that the person selling the fertilizer is also the one making recommendations. And then we think about, as we're trying to encourage best management practices, we actually have evidence in the literature that improved practices don't always lead to improved outcomes. And how do we connect that practice to the outcome? We often end up with increased resource use when we have green or more efficient technologies. For example, when we go from only applying fertilizer at the beginning at planting and suggest that we should split apply, we often end up with higher overall rates of nitrogen application when someone applies at the beginning of the season as well as in the middle of the season. So this is what I've got here, in that we have some evidence from some of our work, but also it's showing up in the literature on farm that we see higher application rates overall. And just recently in this report published in the United States on cover crops, we also see cover crops being not a harvested crop, but more than half of the growers who responded to this survey in 2022-23 season reported that they added extra nitrogen fertilizer when planting maize following a winter cereal crop. So this is a best management practice that's supposed to be reducing nutrient losses, but this is a challenge in reality. For success in policy and market and other reactive nitrogen efforts, we have to take into account the most important factors that affect losses, and nitrogen balance is directly tied to those environmental outcomes. So how can we use nitrogen balance as a metric? It's better than just thinking about rate and telling people they need to reduce rate, because nitrogen balance also considers the crop yield. And so we are going to maintain or improve crop yield rather than just requiring a specific reduction in rate, full stop. So this type of metric also needs to work for farmers, considering their current constraints, and be scalable from field to farm to district to supply chain. And we are working with the, having worked with farmers and with other stakeholders, feeling like nitrogen balance on the field, but also at various other scales is a metric that will work in that case. Some of our research has shown that it's a robust indicator of nitrous oxide as well as nitrate losses. So that's just a couple of examples from our science work. And now we're in the process of moving from that science into implementation. And we want to find and finding something that's meaningful, simple, responding to farm management, working for different crops. So we were trying this out in some different crops, using different inputs, not just synthetic fertilizer, also manure, compost, other inputs. As an overarching umbrella, nitrogen balance provides, is a bit more agnostic toward exactly what you need to do, but then that respects a farmer and their advisors' wisdom and experience in that they can know what works best for their situation. We found that it can be implemented fairly well into existing farm software, and I'll show you some examples of that, but also can be applied in low literacy or low digital access contexts. The safe zone, as I mentioned before, having some maximum level that we would want to not go above a certain maximum level to minimize losses, but also not go below a certain level to minimize mining of the soil organic matter. We're working with partners, and I'll show you some examples within the US Midwest, where we're working with a loan provider with 48 farmers in 2022, increased to more than that for the 2023 season. Field average size is 24 hectares. And in Bihar, in India, 18,000 farmers with a much, much smaller average field size of less than 0.2 hectares. So we've got two very different systems and implementing a similar structure. So in the US, we have collaborated with Farmers Business Network, which is a company that provides inputs and also has software for data management and trying to help farmers make good decisions. The objective of this was to provide a loan with a potential for a rebate for farmers who were implementing practices and meeting an environmental standard for nitrogen management. And so they needed to meet a standard for their fields. After reporting their information, we then assessed nitrogen balance and looked at whether they were within a safe zone. And so this was an opportunity. This financial product for FBN was the fastest selling product of any that they had ever released. And here are some of the results from the data that were reported to the program in 2022 for about 300 fields of maize. Overall, we can conclude from this, like we can see examples of high yield that also have very high nitrogen application rates. So we can see we've got nitrogen balances that range over 150 kilograms per hectare. And some of those have opportunity to simply reduce their nitrogen application rates. No field that received more than 270 kilograms per hectare was able to stay within a safe zone of 75. And no field that received more than 225 in this group of farms had problems with a low nitrogen balance. So that just suggests that this just overall, there's like some kind of guideline that can come out of that. And then more specifically, these farmers all got reports as to where they were in terms of nitrogen balance on their individual fields. So in practice, though, the challenge is also one of balance, given that we only had 1 year of performance data and had to make a decision as to whether these farmers qualified for the rebate on their operating loan. And we had a safe zone saying between 25 and 75, and only about 22% of farms had that 80% of their fields were within that safe zone in an individual year. So taking that information, we want to reward those that met the standard, but also encourage those that fell short to improve and try again. And the question is the falling short because we didn't design this requirement quite right? And thinking about, well, we had been saying we would like to see a 3-year moving average within a safe zone, knowing that there's variability from year to year. So considering the variability we saw in a farm, the standard deviation within a farm, we expanded the safe zone for an individual year so that it was equivalent to what it would be for a 3-year average, given the same variability on a farm. And expanding that ended up that a significantly greater number of farms qualified. And then what they did was also reward those farmers that provided this information by giving them half of what they would otherwise have received as a rebate to say, thank you for participating in this program. we have an opportunity now to learn from this information. You have an opportunity to learn and improve and move forward to the potential to meet the nitrogen management requirement. In India, our team developed a mobile app that was used for interviewing farmers and asked them about the nutrient inputs and crop yields, and it's in Hindi for the application on the field. The image on the left provides details that a particular nitrogen balance score is high. In the middle, this contextualizes a high nitrogen balance score into real-time costs. And so showing someone if their nitrogen balance, for example, this farmer was applying 13 kilograms on their field, more than what they needed in order to meet the safe number that was identified. And if they were using urea, then they're wasting 168 rupees. And if they were using DAP for their nitrogen source, then they could potentially have a savings of over 2,000 rupees. The image on the right outlines that a farmer is applying less fertilizer than crop requirements and recommends that they contact an extension official because we have some concern possibly about soil health implications of mining that soil for nitrogen, for nutrients. So here are some data from 18,000 rice fields in Bihar showing a range of scores, and we've put them into two groups. One where the nitrogen balance cutoff line of about 40, where we would want our average to be, just showing where we again have a group of farmers, just like we had in the US example, of those who have high yields and very high nitrogen balances with a short-term potential to give recommendations for reducing your overall nitrogen application rate. And then we have those also who have low yields with opportunities to think about learning from others in their village, others in this whole program, for how can we improve those yields and yet stay within the safe zone for nitrogen management. Addressing some of those yield gaps, giving an opportunity to improve nitrogen management. We did some testing to see what kind of, we did a selection of a smaller group to do a more intensive interviews of them to think about how some of those in this higher nitrogen balance zone could, what differentiates them from those that are in a higher yield and a safe zone, so we can start to look at patterns there. And so what are the differences between these high yield, high nitrogen balance farmers and those that have a high yield and a safe balance? And again, opportunities to improve. So in conclusion, nitrogen balance in our practice is providing some short-term lessons and also giving us some more ideas as how we can move forward in the longer term. We have a feedback going back to farmers and reporting system for both sets of farmers that are participating in both of these programs, and some of them with opportunities to reduce their nitrogen rates and maintain their yields. And we're also in the process of digging into the more detailed data to explore the implications of different management practices, as well as some of the soil types and how people can adjust based on their situation that they have in their fields, and give opportunity to learn as in your situation. And then we're also doing some work to identify some other levers. Do we just need more extension? Do we need financial incentives? Does it have to come, is there policy that has to be changed? And what are the barriers to people being able to make the changes that they need to make on the farm? Are there market issues and things like that? So thank you very much. And I'm happy to take questions if there's time.
Okay, thank you, Liz. No? Thank you very much, Christina. I think in this conference, we are talking much about how we doing the research, bridge the gap between research and the application. It's an impressive work where we are connecting to farmers, we give them data, which are the most important difference that we found between the American farmers and the farmers here in India
communicate, all these things?
Well, one of the biggest differences is that we have an easier time having direct conversations with farmers in India as an environmental organization than we do with farmers in the United States who have some fear of an environmental organization or interference by government and stuff. And so we've had to develop relationships with trusted partners. I mean, we've done that in both places, but that's especially important in the United States. And so we work with these trusted partners and have to make sure that the data, personalized kind of stuff, I mean, in all these cases, but it's especially more of a concern for people in the United States. And so developing relationships, providing opportunities to, you don't have to talk to me if you don't want to, that sort of thing.
Imagine it's a matter of trust.
Yes,
absolutely. It's on the first speaker. One talk he mentioned for precisely for the United States that which is they order the level of trust of farmers to different type of person.
Yeah, do they trust the university people or the person that is their yeah, that's right. The university is not necessarily the trusted advisor, but the person who's working for the local co-op or for the agri retailer, those or their crop advisors. And it's getting more of the crop consultants are really becoming very important in a lot of these cases.
Thank you.
Thanks.
Thank you very much. We move for the question where indeed okay here the candidate 25 long-term action budget for agriculture.
Thank you very much. Good afternoon, everybody. I'm Hamdi Said. I'm a postdoc at Utrecht University in the Netherlands. I work with Lex Bowman and Arthur Poussin, and I'm going to present on the long-term historical nitrogen budget in the agriculture system in India. I've been listening and learning about this during the conference. So India is the most populous country now in the world, with more than 1.4 billion people. Between 1950 and now, the population grows about 1.9% per annual to meet the growing demands from the population and it was reflected in the self-sufficiency policy, increasing in the nitrogen fertilizers. So the nitrogen consumption in India grew by about 8% per year. At the national perspective, that's between 1960 and now, that increased by 82%, 82-fold. Comparing to the global average is 10-fold increase. So we see the massive increase in the fertilizer use. The cereal production during this period has increased 6-fold times. However, the agricultural land didn't increase that much, which reflects the intensification of the fertilizer use in India. As you can see, the fertilizer use per hectare is now reaching about 140 kilogram in per hectare. However, this fertilizer use is not distributed across India. So that's fertilizer application at the district level. So then the uneven distribution between the northern states and southern states. This also an estimate, this graph from 2000. However, this pattern is still existing till now. The implication of the nitrogen in India, the nutrient imbalance, is also groundwater contamination exceeding the limit of 45 milligram per liter across India, as you've seen. Also, eutrophication and algae bloom in both inland and coastal area. So the task here to quantify nutrient budget, I use an integrated model, which is called IMAGE, GGNM. That's integrated model to assess the global environment, dynamic global nutrient model. It's a part of the IMAGE model, which combines the human and environmental systems and assess the impact of the humans on the environment. It couples different sectors ranging from climate, economy, land, food system, energy systems, and so on. And I use that model results to quantify the nutrient budget, which I'm going to talk in the next slide. After quantifying the nutrient budget from different crops in the agriculture, we couple it in with hydrological models called PCR follow-up web. So to account for the different pathways through the surface runoff and leaching in groundwater, and also the model consider not only the agriculture, point source, and allogenous organic matter, and the aquaculture. This all combined when integrated with the model, so we can quantify what goes to the river water, surface runoff, and also from the groundwater. And also the model can quantify the in-stream process and the transport to the coastal area. The model run at 0.5 degree resolution at annual time step. So to give an overview of the nutrient budget, all of you know about that. So it's simply, in simple term, the budget is the difference between the inputs and the outputs in the system. So in this model, we differentiate between the gross and the crop area. The gross is divided into three main crop categories: rice, legumes crops, and the rest is grouped in the upland crops. And the calculation is done at each grid cell. And the different inputs include N fertilizer, animal manure, biological N fixation, atmospheric deposition, and the outputs is the uptake from crops and the grass. When the calculation for the budget, so when it's coupled with the hydrological model, we can quantify the pathways from the surface runoff, groundwater leaching, and soil denitrification. So once we calculated the outputs, we divided it by the inputs, we can estimate the nitrogen use efficiency. So the point is, in this model, India was treated as a single country in terms of, for example, didn't recognize the differentiation between fertilizer use between the states or the crop production, because the image model combines consists of, it's a global model, divide the world into 26 world region, and India is one region. So the problem, as I'm gonna show, is to differentiate, to consider the special distribution of the agriculture system. So to do that, I consider the India Stat database, I rely on it, and in the crop area, crop production, fertilizer use, to consider this special differentiation. That wasn't an easy task. So it's a private database, and we get a license from it. But data processing wasn't that easy as it seems. So that's one example of for the state-wise for the maize production in India. So you can see here, for example, that some data starts in 2010, but what's about previous data? So it took me some time to figure out that previous data was included in this region, in Jammu and Kashmir. And also this state, Telangana, has no data. So its data was included in Andhra Pradesh. And yeah, that it takes a lot of time to consider the data curation and processing. And also you can see here there's a sudden increase. So I have to look at the files and see what's going on. And that's probably what's a unit mistake. So in some years it's reported 1,000 tons, and in the following year it's in tons. So I have to correct that. So I integrate that in the model and that using distribute, for example, the fertilizer use, the crop production, to see what is the share in each state. After that, running the model, we can come to the soil end budget. So that's the current soil at 2010. So as you can see here, that is the input for each state. And by the way, the calculation is still done at each grid cell level. And that's the output. If we substitute the output from the input, we can get the end budget. So we can see here, the northern state has higher budget and southern state from the other. So that can help us see where the hotspots in the nitrogen budget. If we divided the output to the input, we can get the nitrogen use efficiency at the state level. So we can see here the difference in the in this state, Andhra Pradesh and Telangana. Still, the input is high, but comparing to the output, that's why we have less efficiency. And the same goes to the states. Kerala is an interesting state. You see still high input and high output. So we get high nitrogen efficiency. So that's results is considered the special difference between the states. We run the model considering India as a one state. What I mean here, one state doesn't consider the fertilizer use application between the northern state or the southern state. So you can see here the special distribution is completely different than what we got now. So we get an accurate or close to the reality in the budget estimation. If we look at the long term, you can see here the different components for the input, output, the budget, and the efficiency from 1970 till now. You can see there's a growing or an increase in budget, and also we get two patterns with states with high budget, which is the northern states, the original Green Revolution, and also Bihar and West Bengal, which is part of the Indo-Gigantic Plain, and also in the southern states. So this pattern is clearly still happening from 1970 till now. If we look at the some quantification, the agriculture area didn't change that much over the year. However, the input is increased from 7.6 to 30, which is almost 4 times. The output didn't increase by 4 times. If we look at the budget is almost 5 times, which reflects the high increase in the budget. That's also reflected in the nitrogen use efficiency, which has dropped from 0.4 from 43% now is 31%. So we also grouped India into four main regions. The reason behind that was to distinguish the Green Revolution states from the other states, and the rest is grouped based on the zonal zones in India, just to northeast, southwest, and north central area. So as you see here in the four region, the budget is growing. In absolute term, the southwest region is the highest, contributing to the budget, and we can also see the pattern for India as in the nitrogen use efficiency is falling down. But we can see here between 1970 and 1990 is the reduction is faster than after 1990. Also, some interesting parts here. If we look at the N input is coming from mostly from the fertilizer. If we look into the application rate for per hectare for the fertilizer or animal manure, you can see clearly in the southern region, and the Green Revolution is driven by the nitrogen use, the N use, from the early times. However, in the north central and northeastern, you can see the dominance of the animal manure use, but this is going to change recently. The contribution from the position and biological N fixation doesn't change that much compared to the rest. We also assess the loss to the environment in the four region. So you can see in the north central and south region, the major losses from the nitrification part. The northeastern, it is from the leaching. In the Green Revolution, it is that's a mistake. So it's from the nitrification and the ammonia volatilization. And that's the relative contribution to each of each region and the pathways. So the main conclusion here, as you see, crop production is going up, N input is going up, the N budget is also increasing, but it's not equally distributed across India, so that can give us an impression where is the hotspots and where the places that there is a potential for closing the gap. However, the N losses is also increasing. Then the N efficiency is going down. And here I'm acknowledging the fund, Marian Desti, which is a Dutch-Indian collaboration, funding the project, co-creating sustainable agriculture use in the Indian sub-basin, a multi-scale participatory approach. And thank you for listening.
Thank you very much, Hamdi. Do we have any questions in the room? Thanks for the nice presentation. I am excited about how we get this graded data, because all the results you're showing there is graded now. And the data, I think, is stick-wise. So how do we update that now?
So the data, the input is coming from image. The input is coming from image. The agriculture area, agriculture production, animal numbers is all coming from image. So we use IndiaStat to distinguish between, because the data in image is one number. So we use the IndiaStat to distribute that relative contribution each state. And it's a state level, not district level.
More questions? No? I have a question. You have shown how there is an increase in energy sufficiency in the last 50 years.
50 years.
About 10%. Something.
Yeah.
I wonder what is behind this data. I remember this data by Singh showing that part of the reduction of the energy sufficiency in China was of course associated to gasification and to over-fertilization, but part of the decrease was also associated with a change in the crop mix, a replacement of cereals with more of cultural crops that may naturally have lower fertilizer sufficiency. Do you think that this could have happened here in India? Do you have an idea, or which is the reason behind this decrease?
Yes, thank you. Yes, actually this was part in a paper under review now, showing that the cropping system has influence in the nitrogen efficiency. And I showed, yeah, because if you look at the region, in the northern state, we try systems, which is subjected to losses. And if you look at the southern, there's another completely different cropping pattern. And that's still the higher fertilizer application, but crop uptake is still low, which gives more space for losses. So yeah, the cropping system has influence in that.
Thank you. Thank you, Mohammed. Well, one last question.
Yes.
You were saying that
fertilizer to the field, but still the IUP is down. Your data is showing.
Can you repeat your question?
No, I'm saying that though we are putting more synthetic fertilizer to the fields in comparison to what we were putting in 1970, right?
Yeah.
Still the crop production, I mean, the IUP is going down. What the data is showing.
No, the crop production is.
No, the IUP.
Yeah.
Efficiency is going down, right?
Going down, yes.
So though we are putting more synthetic fertilizer,
more.
Means our plant uptake is like doing that in some way, because like earlier we have this crop rotation system, the legume based. Now, like we discourage most of the parts, so that this could be the one reason for this, IUV decrease.
If I understood you correctly, you mean?
Okay, no problem. I'll discuss this later on.
Okay.
Thank you.
Thanks.
Okay, next speaker, someone you know, see, yeah, from Kenya. However, he's going to speak about nitrogen sufficiency of wheat and then in Kenya. We'll have 30 minutes. We are ready to listen.
Yes.
So good afternoon, everyone. My name is Samuel Njoroge, and I work as a scientist at the Africa Plant Nutrition Institute, based in the Nairobi office in Kenya. And I want to present a bit of some preliminary results on some ongoing work we have going in Ethiopia, looking at wheat and tape cropping systems. And I think this discussion will be a good follow-up to the discussion we've just had about the effect of cropping systems on nutrient use efficiency, especially with regard to nitrogen. So we have been working in the central highlands of Ethiopia, the Amhara region, and this is just a snapshot to give an indication of the sort of farming systems that are involved. These are really, on this scale, relatively small farms, maybe most of them less than 1 hectare. So what you see here, that these are individual farmers' fields, and with highly intensive cultivation, different crops. So It's a high potential area in terms of rainfall because of the high altitude that is there, but highly fragmented. Have a lot of small feed sizes. There's intensive cultivation of the main cereal crops, which is wheat and teff. Teff is a cereal crop that is fairly unique to Ethiopia. Other than it's but then also production of onion is there, especially on a commercial basis. Farmers are really picking up production of onion for sale. Lentil, chickpea are also major crops. And farmers mostly will work to either monocropping of the cereals or sometimes rotation systems. And in the context of sub-Saharan Africa, the fertilizer application rates in this region are fairly high, about 300 kilograms of fertilizer. So it's often possible to find farmers applying about 150 to sometimes 200 kilograms of N, which, in the context of sub-Saharan Africa is fairly high. But then the nutrient use efficiencies are fairly low. And so part of the work that I'm going to show, this is still ongoing work, but we still want to show what are some of the lessons. So the study we had, we adopted the non-farm nutrient omission trial approach. So basically now we had about 32 fields working in one district in this Amhara region. The district is called Minja Shenkora. And then within these districts, you have smaller units like villages. So we selected, so the way this, this area is a hilly area. So on the higher altitude, you have more of wheat production. And then on the lower altitudes, that's where you have more of teff production. So then we selected about 4 villages which are at high altitude, which are predominantly wheat is grown, and then 4 villages where predominantly teff is grown. And in each village, we'll have about 8 on-farm nutrient omission trials, selected based on the findings of a panel survey we did to characterize farms in terms of the general soil type, the perception of farmers about the fertility type, and also how the crops they grow. So trying to come up with general categories that are based on soil type, soil fertility perception. And then now we had this nutrient omission trials on farm. This is one example there that you see. So having the control plots and then proceed all the way as we omit N, PK, likewise. And the last plot we had NPK plus secondary and some micronutrients. And our aim was to assess the magnitude and spatial temporal patterns of wheat and teff field responses to nutrient applications. So we ran this for about 3 consecutive seasons, starting from the 2020 cropping season. And we also wanted to look at what would be the potential effect of rotation crop management on the yield responses and productivity and nutrient use efficiency. And for this particular presentation, I'm going to focus a bit on nitrogen. Of course, with this data, there's much more we are going to tell about the other nutrients, but I think for the interest of this conference and audience, I think we'll talk a bit more on N. So here's just to demonstrate a bit of the experimental design we had. So if you focus at the very first level, we had our first season. So our plots, then we'd have the control plot. So we had 6 plots. So the control plot, then the PK, where you have your N omitted, and then you have your NK with the phosphorus omitted, MP with potassium omitted. You have your MPK with all the 3 primary macronutrients. And then the last plot with the NPK, magnesium, sulfur, zinc, and boron. And then what's happened now in the next season, on the same exact plots, we did a split of each plot. And for example, now in one of the plots, you see that I'm showing an example of wheat, but it's a bit of the same thing we did for teff. So we would maintain half of the plot as the typical practice as in the previous season. So for example, maintaining it as a control, but then the other half will bring in a rotation crop and then apply the recommended fertilizer application practices for that crop. So you see that is what is happening across that second season. And then in the third season, now we flipped it back to the omission trial design. So now again, we come back to, so they are still individually split, but then we have the control, the PK, all the way. And so in terms of nutrient application rates, so for wheat, when we are looking at the main crop that we had in the nutrient omission setup, this is the entire application rate. So 150 kilograms of N, 40 kg P, and then all those other rates. So ideally, this is what you'd have in your plot number 6, which has everything. And then in the other plots, as you omit, then each of the rates will be omitted. So for example, in your PK plot, you'd then have just the PK, sulfur, magnesium without the 150 N. And then what's happened now is when, so again, these photos show, so like in wheat, out of the 32 fields in the second season, now we split, and in 16 fields, we'd have either teff as the rotation crop, and in the other ones would have onion as the rotation crop. And then here, these are the nutrient application rates for our rotation crops. And you appreciate that they are quite lower compared to the application rates that we have for wheat, which I think it will be important when we are looking at the findings later on. And you also know that, mainly the application here, the current recommendation, mostly they apply NP and sulfur. The soils here are fairly rich in potassium, but I think this is something that also maybe over time may need to be considered, given the continuous removal. For teff as the main crop, so teff, the yield potential is much lower than wheat because it's a very small and thin plant, so it easily lodges. And you see from the photos there, teff is there, sort of like a grass-like plant. So nutrient application rates, like for N, is half of what we had in wheat. And then when we bring in the wheat rotation, so this wheat rate is different from what we have in our nutrient commission trial. This is now like the current local recommendation, which is for NPNS. And then we also had chickpea, which we rotated in here. And now to look at some of our findings, especially starting from the first season. And the first thing you see is that, nitrogen is naturally really the main limiting nutrient in this system. If you look at the sort of yields you're getting in your control plots, in your PK plot without nitrogen, basically no difference to what you get in your control plot. So you have an immediate response to N, whereas for the other nutrients, maybe not very strong. Phosphorus a bit, but again for the others, but of course a lot of variability within it. And we also, that's then what we wanted to have a look at. And if you look at the absolute response here for the first season, now looking at each field level. So this cumulative frequency plot, they show each individual fields, all the 32 fields. Then you appreciate the spatial variability that we had in terms of responses. And this is the absolute yield responses in tons per hectare, calculated as the yield that you'd have in your NPK plot in that field, minus the yield that you get in your PK plot. So you see that those are very strong spatial patterns coming in. And in the second season, basically almost a complete overlap of the same. So not a lot of temporal variability. You don't have a shift in the patterns over time as happens in some cases. So looking at that season, so this data that I'm showing here, this is then, we have restricted to the part of the experiments where we had wheat always in the nutrient emission plots. So that season, a bit of a shift in the response pattern, indicating a bit of a reduction in the response. So this is something we want to look at and try to understand what could be driving this. But then now if we start focusing on the rotation system, what you find is that now these are the plots where so this is the data for the third season. And these are the plots where in the second season, we either had onion or teff as the rotation. So now again, we look at the difference in yields between the MPK that had either onion or teff previously, and the PK that had either onion or wheat. And what is interesting is that in terms of the yield response, we don't see any difference. You see, they are fairly, overlapping each other. But what is probably interesting is that because when you look now at the individual yields, we do see differences. For example, these are the yields that then, if we look at now these particular PK plots, where we didn't have any, and we do see that clearly that in the systems where you had onion previously, your PK plot is performing much better. You see those, the yields are more on towards between maybe slight 1 to going to 4, so a clear difference there. And then what also you see is that also when you look at your MPK plot, which had onion previously, again, you have higher yields compared to where you had teff. And I think this is what then is a bit hiding the effect we see on the response, because I think for where we had onion, it's a bit max because you have on one hand your MPK yield goes up and also your PK goes up. So when you try to analyze for differences in response due to your precursor, then it sort of gets lost there. But there's still something in here. And then when we add now, this is the black dots now, this is our MPK yield in the wheat, where we have continuously the MPK plots. You do see that it's not performing as well as when you had your onion or your teff previously. And mark you, this is where we have the black one, is where in those 3 years, that's where we have had the largest nutrient application rates, because this is where we have the 150. And again, now this again comes out when you look at your partial factor, and efficiency, and you look at it and you see in systems where we previously had onion, you have more of about 50% of your fields you're achieving a partial factor productivity of at least 40, which 40 we would consider it something, something reasonable. Of course, is partial, but you see that compared to where you had a tape, which is again a cereal, or where you had your continuous wheat, there's a stark difference. Looking at tape, maybe not as strong as those that we see for wheat. We do see the nitrogen coming out as the most limiting nutrient, but effects are not very strong because TEF is not very responsive to fertilizer application, and also it easily lodges, and when you have a high application rate, so we see that. And then when you look at the yield response patterns, again a bit smaller, but you do still see that spatial effect. You have a few fields which in the first season, no response at all. And then a few fields where the response is almost going up to 2. So some spatial variation. Temporal-wise, yeah, we don't see much changes in the second season, and also in the third season, which is a bit different to what we saw for wheat. Then when we come to look at the effect of the rotation crop, you see that, so here we had either chickpea or wheat as our precursor. And again, similar to what we saw for wheat. Okay, no differences in the responses. But then when we look at our PK, again, and apologies, there's the upper part, the legend there should read again chickpea or wheat. There was a bit of error coming on from the previous graph, so pardon that. But again, you see the effect of, in this case now, that will be your chickpea. And chickpea, you remember the application rate was very low, but again, as a legend, we see a bit of the contribution. Looking at the MPK yield, again, a bit of an effect of having chickpea in the system compared to rotating teff and yes, another cereal like wheat. Looking at your efficiency, we see potential benefits in there of having this rotation system. So yeah, so that is there. And now just to come to the conclusion is that what we observe, we indeed saw very large spatial variability in your response to N, especially for wheat. And something that I didn't mention here is that in our preliminary analysis, we had collected soil data for all these individual fields before we started. And when we look at the soil data and also the selection criteria we had in terms of soil type, we were not able to explain the differences in responses. But based now on some of the additional work we've done, we've been able to see that there could be masked effect, whereas if you look just at the response, you don't see the effect. But if you look at what is happening in your PK, in your MPK fields, you can then start to deduce some effects. And we think that accounting for past crop management can help to reduce the variability and enhance nitrogen use efficiency. And I think then there's room then potentially to manage, because what we have here is basically blanket applications at a regional level that say this is what you apply for all your fields. But I think for improved efficiency, there's room for coming in to say that based on what you had grown, you may either reduce or increase your application rates. And the positive effects we see of rotation crops on yields and nitrogen use efficiency can contribute to sustainable intensification, resulting in positive economic and environmental outcomes. Yeah, and this work has been funded by Global Affairs Canada. Is part of a project we call the Power Solutions Project. We've been running in Ethiopia, Ghana, and Senegal. And just want to appreciate some of the partners we've been working with, and thank you for your attention.
Thank you, Samuel. What time? Because you have no.
Hopefully it's because it was very clear. Thank you.
We have only one question, but we have no time. Why don't include some fixing crop with the weight only in the rotation?
The reason is that we strictly wanted to follow what farmers actually do. So farmers mostly will either they don't grow chickpea in the rich areas mostly. And chickpea is also facing a lot of challenges because of disease issues. So the production is going down and it's been replaced a lot by onion, which is also more economically important for the farmers. Yeah.
Oh.
Yeah.
Thank you. Again, to somewhere. Okay. And then next is our last edition. Unfortunately, yesterday, and then it's here. I will invite here Jose, who is Gabriel. So you have the 5 minutes. I'm going to do your best.
Yeah, okay. I'm going to try.
Okay, good evening, everybody. This is a total change in the subject in this meeting, but you know, all of us base our results and our investigation in lab analysis, and most of them are soil nitrogen mineral analysis. And we know that the protocol say that we need to analyze the sample in fresh before 20 or 48 hours or something like that, conserving in refrigerator. But we all know that we have read a lot of manuscripts, we have visited a lot of labs, most of them keep the sample or freeze it or, I don't know, air dry conserve. And we say, okay, can we do that? What happened is going to have any change? And because of that, we did this analysis, because we didn't find any information about that. So this is the objective, to try to find what happened. And we hypothesize that in some condition, this protocol could be a little tricky. Okay? Because of that, we take samples from three quite different soils, one sandy, one loamy, and one clay loamy. We also try to mix and to provide different situation, adding different kind of organic matter, but also adding different amount of ammonium nitrate, just in order to have very different conditions. One of the sample was analyzed directly fresh, another was analyzed after freezing, and another after air dry conservation. Okay, and we did some statistical analysis. So the results for the nitrate, we see that the first one, no, the arrow is not working, but anyway, we have. Oh, sorry. Thank you. We have here the complete data set. Here is just the higher part, and here is the lower part. So for the nitrate, we see that there are not very lot of difference when we are moving in the lower zone, but in the higher zone, we see that in red is the air dry condition. We are underestimating a little bit our nitrate amount. And for the ammonia, we have something similar, that we have some differences in the higher part, but also in the lower part. Okay. The good news is that when we are analyzing the complete mineral nitrogen of the sample, one side compensates the other, so probably are moving from nitrate to ammonia. So if we are looking for all of them, we are quite good. But if we try to move or to analyze what happened with the nitrate or with the ammonia, we see that freezing and air drying are providing completely different rates. Okay. In this case, we are seeing what happened with the nitrate in the case of the different types of soils, and we see that the kind of soil doesn't introduce a lot of noise. Okay, it's the same for the ammonia. In this case, we we see that there are some difference, but not so large. And again, for the total mineral nitrogen, we don't see so much difference. Okay. As conclusion, soil sample conservation technique is an important decision that could affect the results. Both freezing and air drying conservation are quite good if we are moving in a regular range, so no problem with that. But in some cases, we can find some difference. Also, when we are moving with a lot of organic matter in our soils, it's preferable to go to fresh analysis because the noise is much higher and soil texture it doesn't seem to introduce a lot of noise. Less than 5 minutes.
Okay, thank you, Jose Luis. It's always interesting to see methodological comparison. Probably there is a question in the room. Even we comment, we know more or less the soil that we have and the range, the concentration that we are showing, which there is no problem. We recommend that we can do any of the three methodologies.
Yeah, I think so. Only you need to keep in mind that you kind to be sure that you are moving in this range, and also that in your analysis you only are interested in the total mineral nitrogen. If you are looking for one specific, yeah, could be tricky, and I recommend fresh.
Okay, makes sense. Any other question? Yeah. So I have a question actually.
Yeah.
Everybody have the mic. So for the organic, you said that when you have organic matter or high organic matter, it's better to use fresh samples. How much organic matter are we talking about? And then the other question I had was for the air dry, what kind of temperature will you dry the soils at?
For the air dry, is more or less in the, hear me twice, the 20, between 20 and 30 degrees. So this is the temperature that we had in our lab. For the organic matter, we have tried with very high amount of organic matter, and it's artificial organic matter because in Spain we don't have so much in our soil, so it's artificial. But we have tried also with different kind of organic matters, fresh organic matter, but also thermostabilized organic matter, and more or less the results are quite similar. But we should go further and check in the condition, I don't know, in the north of Europe that can have 4% of organic matter or something like that. Further analysis is necessary, I think.
Super rapid question.
Yeah. Now, so did you leave your material for some time before taking your analysis, or did you take it immediately? Some labs, after collecting the sample can stay in the tank for weeks or months before the analysis is done.
Yeah.
The study is significantly different from when you take your sample, when you do your analysis almost immediately.
Yeah, the fresh was always directly. So we did the extraction at the same time that we put in the freezer, or at the same time that we started the desiccation. So was always is our first moment. So we didn't keep the sample more than 24 hours. Usually 1 hour or 2 hours was extracted.
Okay, I think we need to close the session. I wish to thank you. Thank you to all the presenters for this great session and to the audience. And now we are close the session.
Thank you so much, our co-chairs, for for such an interactive session full of knowledge and new research ideas. I would now request our co-chairs to please join us on the stage for felicitation. I would also request Dr. Suhail Khan to please join us on the stage for the felicitation. All the speakers of this session are requested to please join us on the stage. Please join on the stage. I would now request our co-chairs to please give a token of appreciations to all the speakers of this session. After that, we will have a group photograph, so please be here on the stage. Thank you so much, audience, speakers, and all for listening this session and beautiful and interactive discussion. Thank you all. Yeah. It's now time for lunch break. And after lunch break, there will be a INA research session. So please, I request you all to assemble in the same hall for that session. Thank you so much all. Enjoy your lunch.
Hello, 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 hello. Hello, 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 hello. Hello, 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 hello. Hello, hello. Hello, hello. Hello, 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 hello. Hello, हेलो बंद कर दूं हेलो
चेक उसमें चेक करना चेक चेक और आप
Everybody, please settle down. नहीं बोल दिया उन्होंने स्टार्ट करना बैठ जाओ बस
वीडियो आ गया कोडिंग का वीडियो आ रहा है स्टेज का ओके
Welcome back everyone. Eco. Welcome back everyone. Hope you enjoyed good food. And with a good mood, let's move on to our next session. For that, I would like to invite Dr. Mark Sutton, Professor at UK Center of Ecology and Hydrology and Director of GCRK South Asian Nitrogen Hub, to conduct the session and convey the emerging message of I&I research. So please. Yeah.
Yeah. Okay, everybody. So everybody, welcome to this afternoon's session. We're going to tell you something about the emerging messages from the International Nitrogen Assessment. We've got a conversation piece here with some questions, some presentation, and some opportunity for you to ask questions afterwards. I think you know most of our panel, David Kanter, Wim de Vries, Hans van Grinsven. Apparently we have to explain why we have two Dutch guys on such a small panel. And the answer is which Jill Barron sadly couldn't get here. There we are. David Hooper and Arti Bhatia, colleagues you know. But I introduce here, who you don't know, a friend from many meetings, Urmi Goswami from the Economic Times of India. And normally I call Urmi in moments of desperate panic. Everything's happening. The world is going pear-shaped. We have an event. It's on in 1 hour. Are you ready for us, Urmi? So this was an exception. On this occasion, we actually invited you in advance. Right. So Urmi is going to bring us to order, ask those obvious questions which we as scientists fail to recognize because we're too close. So you have that perspective. Over to you, Urmi.
Thank you, Mark, and welcome everybody. I hope that we I know you guys are scientists, most of you, so but you have to bear this one non-scientist who's going to try and navigate this hour with you guys. We'll start off, Mark, with putting the spotlight on you. And is there another mic? Yeah.
Thank you.
Yeah. I was wondering if you could start off by telling us a bit about this international nitrogen management system.
Yep. So there is the International Nitrogen Initiative. It's a global network. It has these conferences. It's a very light network. But if you look at the world of science policy engagement, you need some, let's say, more integrated set of tasks and an audience who's paying for it, and wanting it. So we spent a lot of time looking to how to do that, and ended up working with the United Nations Environment Programme and the Global Environment Facility, who are very kindly paid through the member states of the UN, building up this thing called the International Nitrogen Management System, for which you can see as a process of science policy support globally. But of course, it also becomes a project at a certain point when they fund it. But the good news, I hope, is very much that the life of the process goes beyond the money of the project, so that in due course, there can be the next steps. And that also means building a partnership with the countries. So one of the things we were first there with the process, the INMS, and one of the requests from UNEP was to develop a policy home. Where's the policy home going to be? What's your relationship with the countries going to be? So that is developed on the way. We're coming to the end of the funded project INMS, and we're going to talk more in a minute about the international nitrogen assessment. There's been money on the table, but there's also been a huge amount of voluntary work from many of you in the room here, many of you online, and others. And we just want to, before going any further, thank you all for your efforts. And it's a slow process, but I hope through these process of new resolutions with the UN, through the member states working together, we're finding that policy home.
So tell me this then, you also have, from what I remember, you have had 2 resolutions in the UNEA. They're both reporting back this year at the UNEA that will start at the end of the month. So can you correlate, where are we with that? I mean, because that's obviously the larger global thing that's happening, right?
So it's been really great. And I think it's fair to say that the support from INMS and also the South Asian NUP has been critical to getting those resolutions, building those partnerships with the governments. And so the first one with India, the second resolution with Pakistan. In fact, we've been working very closely with Sri Lanka. Sorry.
Now, what has the world come to when I know more than you do?
Yeah, that's good. Don't listen to what I say. Listen to what you think I should have said. It's very good that I'm not in the US government pressing the red button, because I'd get the colors wrong. Sri Lanka second, and now we've been working with Pakistan. They've got elections coming up. Of course, the politics is also there. A draft resolution is with the Prime Minister's office. So let's see where that goes. But this has certainly been moving us forward in terms of that. One of the calls already from the first resolution was building together evidence for assessment of the threats and the benefits and what we can do about it. And that is what we're delivering now with this international nitrogen assessment.
Okay, before we sort of move in, I just wanted to ask you a couple more things, just so that we can relate, to relate what the work you guys have been doing to stuff that's happening in the real world. We saw with the Russian invasion of Ukraine, fertilizer prices, and that should have a bearing on the work that you do. And how does it, does it?
Definitely. And one of the things that you'll hear as you go around the group is that we see nitrogen not just as an environmental pollutant, but as a valuable resource that's wasted. It's worth a huge amount of money. And that the more expensive the cash price, the more countries are willing to take action. So with essentially a tripling of world fertilizer prices, that has put so many more countries and so many more stakeholders at all scales saying, what are we going to do about it? Countries which are subsidizing their fertilizer, like India, but many countries across the world have been subsidizing fertilizer. It means when the price goes up, their government fertilizer bill goes up. So the countries become more motivated to do something. And so our argument is, the low-hanging fruit measures, there's an awful lot you can do that put it in your business plans that's actually going to mean you're more profitable by wasting less resource. And that maybe is something just to be very clear about. In the past, we just talked about pollution. It's good, it's really important, but it can be a set up a dichotomy of you're the pollutant and then you're the hated person because you pollute, and that can set up barriers. Whereas saying that pollution is also a waste of a useful and valuable resource is making the point that we can all benefit from this, good for the environment and good for your economic situation. And I think that is a message that's been coming through the INA loud and strong.
Right. So you mentioned this thing about pollution and waste, but we don't recognize nitrogen waste as different from pollution, do we?
We are starting to.
Okay.
So it's been a pathway, and the concept of nitrogen waste was really to say what would be a simple goal? And we came up with the idea of halve nitrogen waste 2018. David will be very happy to point out that it happened in his seminar room in New York University. But it was waste, not reduction of input. If you have a conversation about reduction of input, instantly you set up antagonism because people say we need that fertilizer input to feed the world. But if we waste less of that resource, then it can contribute better to food security. So where's that gone into governmentally? We launched it in late 2018 at the Our Ocean Conference. By 2019, it got recognized in the Colombo Declaration, which was agreed by 14 countries. Since then, Sri Lanka brought that to the United Nations Environment Assembly, and the second resolution recognizes this concept of nitrogen waste.
Right.
It didn't define it because there was, you know how stakeholder agreements go, but we have defined it in another document for the United Nations Economic Commission for Europe. That's an adopted guidance document by 30 countries, which is essentially saying it's all of those losses of nitrogen to the environment, but also including the denitrification back to N2 or other conversions back to atmospheric dinitrogen, not because it's pollutant, but because it's a waste of resources.
Right.
That waste of resources is lowering the efficiency. Lower efficiency ultimately would mean more pollution. Therefore, we reduce that loss, make the whole system more efficient. So we join in that denitrification as well as the pollution.
Right. So we're also, I mean, and one last question, which is kind of like a sideway conversation, but nonetheless, because we don't exist in a world where we exist in a world where several conversations are happening, and in the environment space, the climate conversation is pretty dominant, and when we talk about decarbonization, we are talking about hydrogen, and then when you talk about hydrogen, about how you transport it, then you talk about ammonia, and I'm wondering how does that feed into the nitrogen question, because clearly it's not as benign as the conversation appears to be, or maybe I'm getting it wrong again.
No, so this is a real significant thing. Let's say I would call it a key turning point. That when we started the international nitrogen assessment, people knew about the ammonia car. You can drive a car with ammonia, but it was like a theoretical concept, and people were not really doing it. But with that drive for decarbonization and people finding that ammonia is a great hydrogen carrier, and it's less leaky, and you can stick it in ships and take it around the world and generate critically green ammonia from renewable sources, so in a principle carbon free, and then burn it somewhere else. This is very exciting. But what, from an assessment point of view, the projections are suggesting that the world might be having 3 or 4 times the amount of nitrogen by 2050, whereby the burning of ammonia is an even bigger source than the fertilizers. Now, this is really exciting to get people to wake up because, hey, we're going to have triple, quadruple the amount of potential risks for pollution. Not all of that will be pollution, but so far the technologies are not there to ensure they're completely clean. So this is making it clear that it's gone beyond agriculture, it's gone beyond normal industry, it's a multi-sector world, and it's, of course, integral with the climate change discussion.
So basically, we can have net zero, but you can, but only if you're talking in carbon terms, but you will not have climate neutrality because you will be spewing nitrogen.
So that's the question, still for more work. But in principle, the question would be, you've got those extra nitrous oxide emissions. I'll let one of the other panelists answer whether they think the trade-off is there.
Yeah.
I would say, for the moment, to say it's actually going to be better or worse, still needs more assessment.
Okay, so now that we've sort of set the stage and you've answered all my questions, I'm going to turn to Hans because, sorry, I should have done that.
No worries.
Because you know, Mark spoke a lot about assessment and that requires tools and guidance because you can't have, you know, everybody doing their own thing, right? So maybe you could take us a bit through the kind of, you know, tools and tools that are available to actually do the measuring.
Okay, I will give you a brief outline of what we did. If we want to do an international assessment or any international project, the success depends on agreed methods. So the first thing you have to do is to discuss which methods are on the table, which ones are good, which ones are not so good. And if you agree on that, you have to write that down as a guidance so all the participants in a project, because otherwise India and the Netherlands will come up with results and say they are different, but sometimes they're just different because they use different methods. This discussion has been going on all week in different rooms, and that's really a key factor for a successful international project. So we had a special work package on defining these methods that we need to do an international assessment. And the first one is, and I will talk a little bit in more detail about it in the presentation, so not sure how much we give here. First thing is you agree on which impacts are recognized in all over the world. And you need a systematic, structured approach to define these impacts. The second thing is that you need to define indicators, which indicators you need to characterize a country or a sector. That's what we did in another project. We discussed on how you measure nitrogen pollution and nitrogen emissions. That was also one of the projects. There was one on costing. That's the one I did myself, so that's very important. Is how you put a value on an impact, because you have impacts on human health, you have impacts on biodiversity. But if you have both, how do you compare them? How do you say which one is more important than the other? Politicians have views on that, but sometimes science can help to weigh these different impacts. And the final one was the models. So
yes,
the models, and that Wim de Vries on my right-hand side was in charge of choosing a set of models to do the global scenario analysis. So that was the 5th part of the work package on methods.
right. But you mentioned that how there's discussions happening in rooms that happened here, discussions that happened here yesterday. But for your current project, you do have agreed or
Yes.
and those are going to be for any future international projects. Is that the gold standard now?
Well,
you're hoping.
Well, you cannot enforce guidance documents on people, but if the guidance document is good and ours are good, we think then it's free for everybody to read them and to use them. But of course, they are used for this project, INMS, but we hope they will be used by many other projects, international projects.
So your guidance, the guidance documents that you all have developed is like what IPCC does for climate change.
Exactly.
So you're like the IPCC of nitrogen.
Exactly.
Wow.
But you're modest too.
Yeah, very modest, I must say that. Okay. Would you like to give a better sense of any, you spoke about costing, which you did yourself. Do you want to delve a little bit deeper into it? Because it seemed interesting when you talk about, impacts, or is that super secret and you don't want to talk about it?
No, we don't have super secrets, but it's all about what people or businesses or voters are willing to pay to prevent a certain type of pollution.
Right.
So you want to know that, and sometimes politicians or businesses don't know that. So they just say we want to protect human life, or we want to protect biodiversity or marine ecosystems. And what we do is we do surveys. We can do surveys. They did huge surveys, for example, for the Baltic Sea, to ask people about how much they're willing to pay to prevent pollution of the Baltic. And you can use these surveys to also make an estimate of how much people in India would be willing to pay for protecting, for example, the marine environment in India.
Right.
And we can do it for all these impacts. And this gives you a hand on how you could weigh these very different impacts.
So would you be the person who I mean, with the document that you made and given your expertise, be the person who would be sort of putting it out in real terms, the impact of this hydrogen question that I asked Mark? Or no?
No, I would not do that.
Is that because you're trying to just say, okay?
Well, it's a different thing. I mean, sometimes you need some certainty on the impacts. And what Mark said about this hydrogen and ammonia issue is we are very unsure about how much pollution it will cause.
Right.
If it's done super well, then maybe the pollution impact is small.
So he's the guy who's going to be able to model and tell us what kind of pollution is there. No? Okay. Yes, you can.
Make a quick addition here. Processes sometimes take time, and this international nitrogen assessment has taken time. In setting up all the scenarios of the view of the future at the beginning, we did not take account of this, I'll call it the ammonia transport revolution.
Right.
Was not in there. and it's happened during the life of the process. So it becomes an emerging message from the assessment, but much of the quantification within the core models, it will not be there. So we have to say, on top of that, don't forget this is a key emerging message.
Okay, so like basically that's the next thing, because this is an evolving area.
It's rolling.
Right, right. Okay, so I'll now ask you to pass the mic on to Wim, and you do the sort of global modeling, right?
Not me, but let's say
Yes.
a whole group.
Yes, when I mean, in this semicircle, you're the guy. Okay, so could you give us a sense of all the, what do the models tell us? What is the, I know it's a super science thing, and for me, I mean, you're the scientist, I'm not, so I'm going to leave it to you.
So the question within INMS was, what is the spatial variation of all the impacts of nitrogen? The benefits, food production, but also the threats, like water quality impacts, air quality, greenhouse gas exchange, ecosystem soils. That's called wages. And then the idea is, how does it vary over space? And what are trends in time? Now, if you want to know it for the whole world, of course, only measurements is not enough, because there are regions where you do not have enough. The second thing is, with measurements, you cannot make predictions. You cannot say what will the future be. So that's the idea behind modeling. And what we now did is then first identified models that are able, first of all, to make predictions based on narratives of what do we expect for the future. David Kender was one of the persons to make those narratives. What will be the population increase, possibly income increase? How will that affect food demand, energy demand? And then it affects, of course, the number of the land use, fertilizer use, livestock, and through that, the nitrogen inputs and emissions. And then that went to other models. Now, there are a couple of models who can do that, only limited, and we selected them to compare. And then there are limited models that can then calculate what happens in agriculture, what's emitted. Then there are limited models, what's deposited, and that whole set has been, let's say, identified and connected. That was the document as on methods. And then we applied it, and the results are now available.
Wim, I wanted to ask you, you wanted to run us through some slides, didn't you not? Would you want to do that now?
If you want to.
Yes, please.
Okay.
Did you have slides as well? I'll come back to you then. I'm sorry.
That's no problem.
I forgot.
That's all good. Slides.
So,
there's something you have to answer.
No, image and messages is number 2. This one, yeah.
Comes in, and this guy says,
Thank you.
This guy who does, I mean, basically, that if you don't use fertilizers, then you will be able to feed 4 million people less, or 4 million people will have to drop off.
So this is a good point of discussion.
Yeah.
And the world is, of course, more nuanced than that.
Yeah, so I was wondering,
Happy to answer that.
should I throw it to you, or?
I'm very happy to answer.
Okay.
Now, come back.
Well, what you see here is a very full slide. That mentions what was the aim of what we called Part C of INMS. That's the Global Integrated Assessment across the nitrogen cycle. And the purpose, as I mentioned already to you, was modeling the spatial and temporal variation of impacts of nitrogen fixation. Water quality, air quality, greenhouse gas exchange, biodiversity, and soil. And partly look into the past, 1970 until 2010. And on the other hand, look into the future with a couple of scenarios. So-called shared socioeconomic pathways, RCPs has to do with climate change and all kinds of N options. And what you see on the right-hand side on the top is the N cascade, the famous picture made by Mark Sutton, show all these impacts. And on the bottom, you see all these models I was discussing when I was asked for, saying on the left-hand side, you see something like narrative scenarios. There are a couple of models like called Image, Globium, Magpie, that can change those narratives in land use changes, livestock changes, etc. And that then goes to other models that calculates nitrogen budgets for agriculture, going into air quality models that calculate the deposition, to models that calculate the river export, and so on. So this was this whole set. And here you see an example on the left-hand side of first changes that happened in the past from, here we started even in 1850, but look specifically to 1970 to 2010, on ammonia emissions, NOx emissions, and greenhouse gas emissions, N2O, nitrous oxide. And you see all kinds of sources, but the main thing, of course, is that you see there's a big increase in it. And on the right-hand side, you see on the top the impacts on losses to rivers, to groundwater and surface waters. So the key point is a massive increase in losses between 1850 and 1970 already for NOx and ammonia, and for ammonia even higher between 1970 and 2010. And then we predict the losses to all these impacts I mentioned up to the year 2050 for 7 so-called scenarios. Now, I can't go into the details, but there are scenarios related to the development in all kinds of developments with fossil fuel use, land use, diets. That has to do with all kinds of N options. So let's say main differences. And this picture, that's a complicated picture on the right-hand side about what does nitrogen do to greenhouse gas exchange. Actually, I presented that at one of the 4 places. And why do I show this? Not only because I was in charge of this work, but also because it illustrates nicely what you have to connect before you can make this overall impact of nitrogen on warming and cooling impacts. It starts at the top with agricultural inputs, which are predicted. Industry, transport, and biomass burning both give ammonia and NOx emissions, and directly N2O. Not only